All right, everyone. I think we're going to go ahead and get started. Um, Good morning, everyone, and welcome to UC Davis. On behalf of the UC Davis Coastal and Marine Sciences Institute and our partners at the Delta Stewardship Council, I am really excited and delighted to open today's symposium, Accounting for Blue Carbon in the Bay Delta Science, Policy, and Practice. So thank you all for being here and for bringing your expertise and curiosity to this event. For those I haven't met yet, my name is Alyssa Griffin. I'm an assistant professor in the Department of Earth and Planetary Sciences and the Bodega Marine Laboratory here at University of California, Davis. My research focuses on coastal and nearshore carbon dynamics and the cycling, storage, and transformation of carbon within and between nearshore ecosystems, and thinking about how those dynamics can inform and underpin just and equitable climate solutions. So I'm particularly excited to have brought together this really amazing group of speakers and attendees across a variety of sectors and agencies to talk about blue carbon in the Bay Delta system. First, I'd really like to thank the planning team and especially Moose O'Donnell and the CMSI office for hosting all of us. So hopefully you'll have a chance to meet the planning team here today. They've been instrumental in making this event happen today. I also want to thank all of our speakers for taking the time to attend and share their knowledge with us. I wanted to just make a few remarks about coastal and estuarine ecosystems. So coastal and estuarine ecosystems in San Francisco Bay and the Sacramento-San Joaquin Delta are not only ecological treasures, they are dynamic biogeochemical systems with real potential to contribute to climate solutions. But realizing that potential requires informed and transparent collaboration across science, policy, management, and community leadership. It requires accurate carbon accounting, a clear understanding of trade-offs, and a true and honest engagement with who benefits from and is able to participate in climate solutions. So today really brings together researchers, practitioners, policymakers, and community partners to advance this shared work. So I really want to encourage everyone to ask questions, build new connections within this room today and beyond, and think boldly about how your expertise can contribute to effective and equitable blue carbon strategies in the Bay Delta and beyond. So a few logistics for today. There are a few agendas on everyone's tables outlining our schedule, which is going to begin with a keynote and Q&A session. It will then be followed throughout the day by 3 sessions that will end with a panel-style Q&A with the speakers from each session. We will have a break for lunch and also small breaks throughout the day to keep everyone's stamina up. There are snacks, drinks in the back of the room, so please help yourself. This hallway here, that's where the restrooms are, as well as the, drinking water if you need it. And if you have any questions, you're welcome to locate someone on the planning team, myself, Moose, and others. It says planning team on our name tags, and we're happy to help you with whatever you need. If you're looking to connect to the Wi-Fi, UCD Guest is the open network that everyone can access. So again, I just want to thank everyone for being here and investing your time and energy into today's conversation. And I'm really excited to see what comes out of today. So without further delay, I'm going to introduce our first speaker today, our keynote speaker. Juggling computers here. So our keynote speaker this morning, I'm very excited, is Lisa Marie Wyndham Myers. Lisa Marie is an ecosystem ecologist with the USGS Water Mission Area and is currently on detail at the state of California as the Delta Lead Scientist in service to the Delta Stewardship Council. From early work on ecosystem impacts of invasive plants, she has focused her last 20 years on nature-based solutions at the land-water interface, especially for climate risks and water contamination. In 2018, she led a global team of 93 academic agency and NGO authors in publishing the first book of its kind, A Blue Carbon Primer, The State of Coastal Wetland Carbon Science, Practice, and Policy. Sounds familiar. And this book was developed to improve understanding of the climate context of coastal carbon cycling. So with that, I'd like to once again welcome everyone and welcome Lisa Marie to get us started today. Thanks, everybody.
Great. Thank you so much, Alyssa. And I recognize you. You ran our project last fall. I'm so happy to see this room so full. And I can't believe we have this amount of brain power in the room to really pull our field together and start moving forward. One of the hardest things about blue carbon is wrapping your head around it. It is like the elephant in the room. It's so huge in so many dimensions, and we ogle at all of these different pieces. Atmospheric chemists say, wow, carbon dioxide emissions are huge, or uptake is huge. And then they say that the hydrologists say, wow, dissolved inorganic carbon export is huge. Same for carbon accretion rates from soil scientists and carbon densities. They're all large. And then if you go the next step, there's also ecologists saying, wow, look at the high respiration rates. And then don't forget about the methane. It's the tail that wags the dog or the elephant. And so there's a lot of carbon moving around in estuaries, changing forms, coming in and out. And there's all these moving pieces, and we don't typically focus on the whole organism of the elephant. We focus on these little pieces. And a lot of this is about different forms of carbon: solid, liquid, gas, energy. And being able to talk about relative fluxes, timescales, spatial scales. There are soil processes that we have to look at alongside atmospheric processes. And so it's complicated. But using the scale of an elephant and global averages, I want to just put this in perspective. There's 1/20th of an elephant in every cubic meter of soil in terms of CO2 emissions. And in the US, each of us is emitting 20 metric tons of CO2 per year. So that is basically like it's the equivalent of 200 meters squared of wetlands, soil. Anyone that's flying, anybody going anywhere this summer? Yes, okay, for us, we have to offset ourselves a little bit more. But our target carbon footprint for the Paris Accords is actually 1 elephant. We're all emitting 10 elephants. So one way that you and I today can start to move forward is protecting 180 meters squared of wetland. And then we've got 4 billion square meters of wetlands here in the estuary to deal with. So let's get to work. If you're wondering, yes, you can see human actions in these large global CO2 signatures. The Keeling curve, which has been funded through all sorts of agencies to keep it going all this time. There's so much information in those wiggles. You can see the COVID effect. Let me see if I can. You can see the COVID effect with a little flattening and during less combustion, and then suddenly a bump up as the economy is recovered. There's the Pinatubo effect. There's the Indonesian peat fires of 2015. That's a huge respiration bump up. Sorry, it's right about here. And we also know that we can bend the CO2 curve with nature-based solutions. Methane is also rising, and it's now become 30% of our climate problem. And that's the variability that's really interesting in here is actually driven more by weather. So for example, we have this Pinatubo bump from 1991, and then this flat period of cooler, drier conditions. Then we have some warmer, wetter conditions that are leading to a longer wetland duration and wetland extents in Africa, Asia, the Arctic. And the COVID bump actually caused more methane emissions due to an exceptional wet period of El Niños, but also the lack of hydroxyl radicals being emitted during that period to then break down that methane in the atmosphere. So even with just parts per billion quantities of methane rising, it has such a big effect, basically 25 or 45 or 80, depending on what time scale you want to use, that much more times more effective than CO2 emissions in terms of having a warming factor. And then the rise of the rise of nitrous oxide is an issue as well. And then, of course, that has 200 plus times more. And I don't know if we're going to hear about that from Tyler, but maybe we will later in his presentation. Trying to move, I'm going to move to this thing. Great. So let's just talk about this, one of the elephants in the room. Do we have to have an economic catastrophe to bring on environmental benefits? Do we have to see that cost? No, there's a false narrative that we have right now about growing economies needing to have high emissions, and that there will always be this direct trade-off of environmental goals and economics. And I want to just point to California, where we've been so progressive. Our CO2 emissions are actually falling as our gross domestic product is growing. So our state is very progressive on greenhouse gases and on nature-based solutions. People are self-taxing in order to have to get to this lofty goal of net neutrality, and our state is very active in monitoring this as well. They've shown that nature-based solutions are a big part of the solution, and even with wildfires, nature-based solutions have already overcome those huge mega fire emissions in California. So even the rate, if you can see here. Sure, I'm going to hit the wrong button, so I'm just going to point to it. You can see that the rate of emissions per dollar gained is actually growing. So we're doing something right. Let's talk about blue carbon. It's one of the best nature-based solutions anywhere on the planet, which is really, the term is really just a term for coastal carbon in a climate context. But its science has taken off like a rocket ship in the last 20 years. The coastal ecosystems that we're all thinking of have always had attention. Geologists and ecologists, giants of science, have always talked about carbon cycling, but through things like about carbon burial for resilience to sea level rise, or carbon productivity to feed fish. But when climate concerns emerged, and there was a lot of attention on forests and stuff, it was Gail Chimura and company and Carlos Duarte that really highlighted, hey, these coastal sites are both mangroves, marshes, and seagrass in particular. They accumulate carbon faster than tropical rainforests, and it's underground, and they don't make methane. So we just need to put a little more attention into those from a global perspective. So NGOs really pushed the needle on this to save coastal ecosystems, and they were a little nose over toes pushing us forward, but the scientists did catch up, and I want to say that UNEP, of course, coined the term blue carbon. The beauty of us catching up is that we were then able to get blue carbon into nationally determined contributions in the Paris Accords in 2015. 29 countries committed to this. So we really moved the needle there, and it came about because of all of these collaborations. And one that I want to really highlight is the Coastal Carbon Research Coordination Network that's created this Coastal Carbon Atlas that people use. And I want to highlight that that's how growth happens in this field, is when we start sharing data and looking at the whole picture. I'm going to highlight here just the blue carbon primer, just to say that we were scoping it literally 10 years ago, came out in 2018, and 2028 is around the corner. So if anybody wants to do some updates, I welcome them to do that. So blue carbon ecosystems have traditionally been coordinated as just the big three: marshes, mangroves, and seagrasses. But because of their globally significant soil stocks, that's why they got attention. We've really expanded the definition of blue carbon to be any ecosystem that's affected by sea level rise or marine influence. So pushing into the upper estuary and out to the coastal shelf. Here in our estuary, we obviously have tidal marshes still, and we have seagrass meadows to be restored, but we also have coastal peats that can be protected by rice agriculture or planting managed wetlands there. That's Jared in the lower right corner. You're not seeing him this morning, but you'll see him tomorrow. He's with this enormous soil carbon pool that is one of our greatest intervention opportunities. There's an estimated 100 teragrams of carbon in that soil still remaining. And then on the ocean side, there's a big push on kelp to understand where their carbon is ending up in the ocean. And on the other side of the estuary, there's floodplain restoration. And that's more depositional mineral soils, but there's a substantial biomass there to make up for it. And I have to call out the Delta Carbon team in particular, because they're bringing on the collaboration that's necessary to move the needle on those upper estuary opportunities. And I hope everybody here and online would consider joining them. So how do we estimate the greenhouse gas benefits of all of these interventions? The first step is inventories, and that's usually done on a stock change approach. When you have a map of approved activity data, which is often annual land use change, because it's more easily mappable, you can then couple that with emission factors that are binned for given changes, and it's kind of like paint by numbers. You might have some parts being wetlands remaining wetlands, which actually is the dominant type, wetlands turning into agriculture or agriculture turning into wetlands, and then there's different emission factors for those. And then you do the math, and then you'll end up with like the amount of removals, which is negative, or the amount that's emitted, and that's positive. For scale, the new California Air Resources Board inventory update for natural and working lands shows that wetlands are 2% of overall removals in California, which pales in comparison to forests, but there is a re-wetting goal of 5,000 acres in the Delta, so wetlands maybe will get their moment then. The default values that are used for Tier 1 and Tier 2 approaches are pretty stable. We know those values pretty well. It's Tier 3 where we have actual models of carbon emissions, and those are especially important for wetlands remaining wetlands. Again, we have so much of those. And most of the country is seeing wetland lost in their coastal zones. The Bay Area happens to have tidal wetland gains. We should be really proud of that. Okay, so how do you wrap your head around verifying these emissions or changes in carbon stocks? Because soils dominate wetland carbon stocks, because they're measurable, and because avoided loss is such a big part of the accounting, we now know a lot about soil carbon. It's particularly the carbon densities in wetlands. Big syntheses of data have been instrumental. We know that carbon marshes average between 25 and 28 kilograms per cubic meter. It's over 10 times higher than any upland soils, and it's due to high preservation of carbon in anoxic soils. We know that the two factors that go into carbon density, bulk density, so weight per volume, and then percent carbon, which is often measured as loss on ignition by combusting the soils, those are inversely related, so that the range of values is quite narrow, and there's a trade-off of those as you go down core, which makes for a consistent value with depth very often. And you can see that in the US in these graphs that are on the right-hand side from Jim Morris and Jim Holmquist. We know the distribution of data is narrow, it's normally distributed, and there's not a long tail in coastal wetlands like there is in inland wetlands. We can see very similar distributions regardless of the scale of analysis, whether we synthesize data across the US or using a global machine learning model by Maxwell, or a synthesis focused on Pacific Coast, for example, by Chris Jenisek, who's over here at this table. So let's look at the synthesis that Chris led. From Alaska down to Mexico. We've got 5 major coastal wetlands represented: tidal flats, seagrass, emergent marsh, mangroves, and tidal swamps. And we can see a mean here for the tidal marshes of about 25 kilograms per cubic meters for marshes across this whole gradient. Tidal swamps and mangroves are a little bit higher. If we just look within the San Francisco estuary alone, just so you know that value actually becomes 27 kilograms plus or minus 11. The most interesting part of the analysis is on the right, and it's that local variability is more important across this big region. Not the regions themselves, but the elevation within an estuary, and things like grain size, like sands and clays, which often are driven by hydrologic controls on deposition. And that also was a finding, by the way, of the Maxwell global machine learning effort as well. The local influence here in the Bay is clearly seen here in our ecosystem for the Delta, whereby our soils here are going down 8 meters back 6,700 years. They're all about 50% higher than the estuary average at 39 kilograms per cubic meter. These tidal wetlands in the Delta are above average. They're especially carbon dense, and since 95% have been converted to agriculture, we have a huge opportunity on our hands for climate mitigation and nature-based solutions through avoided loss of any remaining peat, and restarting peat growth, a process that has operated for millennia. Judy will certainly focus more on this this afternoon. So with all these local data sets and model building efforts like MEM and WARMR, the two that you're seeing here, we can track soil carbon very well in this estuary and even predict future losses or gains with scenarios of sea level rise or episodic disturbance or sediment enhancement and so on. Marsh cores are the archives of the past, so if we build models with these local insights, we can model wetland resilience and tipping points for marsh drowning. These physical models of carbon accretion are quite good and in agreement, but there is uncertainty around the carbon fluxes associated with natural fluctuations and spatial variability. Jim will likely hit on some of these forecasting tools this afternoon as well. So even with uncertainties in carbon accretion, they definitely pale in comparison to uncertainties around methane fluxes, both freshwater and saline marshes, and lateral fluxes associated with transitions to open water, with either erosion or drowning of marshes. So what happens to that soil carbon when it becomes open water? Does it stay in place as a buried peat? How fast does it erode? The fate is very poorly known. Wetlands remaining wetlands can also have dissolved flux of inorganic and organic carbon, and those can be huge, from 50 to 99% of the carbon that's produced, that's photosynthesized, can be leaving the system. So what is the fate of those compounds? Tackling those big uncertainties, again, CCRCN to the rescue. We know now from the synthesis that was led by Ariane Arias-Ortiz that we really need 3 salinity classes, not just fresh and salt, to map methane emissions. And thanks to SFEI's Eco Atlas, we actually can do that mapping now. This synthesis used a huge data set of chambers and eddy covariance data to find finer scale bins of variability in methane emissions. The first thing the study found is that there's a huge difference between 0 to 5 ppt and 5 to 18 ppt. So fresh and oligohaline up to mesohaline, meaning that just a little sulfate goes a long way. 5 parts per thousand, the mesohaline conditions, like we have in most of Suisun brackish marshes, is a really important cutoff point. That little bit of sulfate can reduce emissions 80 to 90%. It's also showing us that air temperature is really important. So that's a mean air temperature, and it's increasing with climate change, and that might actually push us into the next bracket in the next 50 years. Our impounded marshes are different. The subsidence reversal marshes are actually little methane machines. Their rates are very variable, but with the average of 60 grams per year, there are some of the highest emissions that are measured within the entire FluxNet network with eddy covariance. And that's an order of magnitude than any productive marsh would ever be able to compensate for by sequestration in the short run. And this is why we really need to focus on metrics like crossover times to talk about the long run. What's our goal here? So we don't have short-sighted management decisions. So lateral flux, the rate and fate of these fluxes are outside the boundaries of wetlands and they're poorly known. Those carbon fluxes may not be all that bad. Allochthonous carbon coming down from the watershed can build marsh elevations. Exports of carbon from marshes and some allochthonous carbon is also just passing through on that land-ocean aquatic continuum, LOAC, and can end up feeding fish or can end up sinking into anoxic marine sediments. Any DIC, which is basically CO2 that's dissolved in water, and if the pH is right, it's CO3, so it's alkalinity. If that DIC doesn't degas into the atmosphere on its way out to the ocean, the mixing of that DIC into the deep ocean can be another removal term. So the ocean sink is very poorly constrained, and it could be as important as the land sink, but we've only been focusing on the land sink in these circles. Tomoko is going to talk more about this issue of boundaries and fate, and this again is possibly some of the most important carbon for us to think about. It's a large volume that's leaving the estuary, and we don't know its fate when it gets to the deep blue sea. So methane and lateral fluxes that are challenges that we're working on, but where we really have made progress in the last 20 years is in inventories and stock changes for estimating accretion rates and avoided loss, which are mostly addressed with mappable bins and emission factors. Can we do better? Well, I certainly hope so, because here in the Delta, we have some of the best data sets that are available, and we need to improve accuracy and precision for inventories and forecasts across the whole landscape so that we can get into the market for carbon, and also agriculture and forestry communities are way ahead of us here, and I think we can start moving the needle there. We have a lot of potential interventions on agricultural lands, on peat soils that can reduce greenhouse gas emissions, and many of which Steve will talk about later. Actually, I think the next talk, or this morning. And they are important because they're 80% of our coastal lands that are below sea level, and thus they're also the most likely to stabilize carbon in our estuary for millennia, or even in just the next 40 years, which is what's required by the market. So let's talk about the market. There's a fabulous lock setting that won't let me go forward again. So no worries at all. So anyway, talking about markets, we're going to talk about wedges. And so you may have seen, thank you so much. Thank you. We have to recognize that all markets are dependent on models. And specifically the difference between a business as usual baseline emission versus those that are after creditable interventions. Communicating these wedges of opportunity has been done by forestry and agricultural climate practitioners, but we are slow, and we need to pick up the pace because we actually have a lot of benefits to share and to highlight, and a lot of opportunities. So this slide is poached from our colleague Steve Crooks, and it's showing a lot of different ways that climate benefits can be achieved. So for example, I just want to show you with my pointer, but I can't do it, but I think we'll just talk it through. If we work together pointing to this portfolio of opportunities, we might be able to highlight all the different pathways. So in the Pastures quadrant here in the upper right, we have kind of the best case scenario. We have a site that's a net sink, a site that's a net source that is now becoming a net sink for greenhouse gases. A good example of that could be the restoration of the drained peatland at Dutch Slough that now is sequestering a lot of carbon. There's also the lower right, a net source becoming less of a net source by re-wetting the soil, reducing carbon dioxide emissions, but perhaps having a little methane produced as well, like, for example, rice agriculture. Then consider an ecosystem here on the lower left that's a small net carbon sink, like a wetland struggling against sea level rise that we add sediment to enhance its elevation and ability to support marsh plants. And then keep up with sea level rise. And then finally, we can consider a neutral site that's neither greenhouse gas source or sink, upper left, like with planting seagrass meadows, so carbon can once again be sequestered into bay sediments. These wedges are important communication tools, Ironically, there's no little wiggles of the real world, and there's no uncertainty metrics on here. But this is the kind of tools that we need to be better at to communicate, and we can do better here by integrating our knowledge and prioritizing science needs to get those wedges clarified. These markets today need these models for policy implementation, and that includes having confident verification of additionality, permanence, and leakage, and we're going to hear more about that from Barbara this afternoon. And this is just hilarious. Oh, here, I found the button. So let's just talk about towards modeling. Again, we are very well poised here for bespoke modeling of our sites because we have so many different interventions here in the estuary that are being monitored. We have the densest network of eddy covariance towers in the world. They are state-of-the-art for measuring gas emissions, whether it's carbon dioxide or methane or evapotranspiration water. We're getting there for nitrous oxide, not there yet. These direct measurements, taking samples every second, 24/7, they're showing us that we have the opportunity for very high uptake of carbon dioxide in restored wetlands, and we're also seeing that we have a little bit of salt in this Sassoon Marsh area that's keeping emissions low. And on the contrary, on the right, we're having higher methane emissions in the fresher delta. And coupled with measurements of elevation gain, we can show that the restored wetlands are growing in elevation and thus reversing subsidence. It's happening across the Bay Delta. Not only are the data sites abundant, they're also long-term. So we can show that restored wetlands are growing in elevation, but they're also seeing a decrease in methane emissions. That was something that Kyle Delwich just published last year. Two areas that really need our help and confidence in using the eddy covariance data is better partitioning of the carbon dioxide that's being measured, NEE, net ecosystem exchange, partitioning it into photosynthesis and respiration, and then also incorporation of physical transport, including lateral fluxes of carbon from these systems. So that is one reason that I get particularly excited about Patty's peppermint model. It's so useful because it might be able to get us there for marshes, both tidal and non-tidal. There are so many pieces of the elephant that need to be put together, and her mechanistic data model fusion approach with remote sensing and dense data sets from atmospheric and lateral fluxes is the best step forward that I've seen. There's a lot to tackle. Methane variability through time, allochthonous inputs, alkalinity export are three of the most difficult. But collaborations across disciplines and with other estuaries are helping build these models, even with machine learning. So models of seagrasses and kelp and floodplains and even rice might be a little bit different, but they still benefit from comparison with this model and integrated wetland models in general. I'm going to encourage us to think about our work and how it can be integrated with progress that others are making, and not just considering all of our projects separately. Rather, we need to start thinking about what we all have in common and also where our biases are, because we might not be measuring all the fluxes that are important. So in the next 8 minutes, I want to suggest another route to being able to assess carbon sequestration across the whole matrix of land uses. And it's based entirely on how carbon is preserved, rather than focus on each particular wetland independently. We know that respiration is the key, and that regardless of photosynthesis on site, it's relative respiration that controls the rate of carbon sequestration. A first principles approach to respiration allows us to address all potential interventions and also avoid compounded uncertainty when you're integrating all these high fluxes and you're looking for that net residual of carbon sequestration. Wetlands are terrestrial aquatic interfaces, meaning that we can learn a lot from upland and marine literature about how carbon is stabilized in soils and sediments. And I have to credit the Smithsonian's Pat McGonigal, who's my partner in crime on this, and also the source of the mummy picture. As we can see, all kinds of carbon can be preserved. We often think about mechanisms of preservation like lack of oxygen or lignin content or acidity or cold temperatures, all leading to carbon preservation in some way or another. But in coastal systems, it may be the case that All of those things are controlled by hydrology. So let's think about respiration. How does it work? So stay with me, just going back to high school biology for a second. The amount of energy that any organism gets from respiring organic matter, including us, is known as the free energy yield, or delta G. And that energy is letting organisms grow and reproduce. It's also a proxy for decay rate of organic matter, which is the food or the electron donor that's getting respired or eaten. At the top in black, oxygen respiration yields the best return of free energy. So aerobic organisms will always win in a competition if there's oxygen present. The redox ladder, which often coincides with different soil depths, is a way to show how delta G decreases as systems run out of electron acceptors. If you go down this pathway, you'll see that microbes that are using oxidants other than oxygen, nitrate, then manganese, then iron, then sulfate, sulfate reducers are only getting about 43 kilojoules of energy per mole of organic matter. So they are very poor competitors with aerobic respiration. However, they are good competitors against methanogens that are only getting 20 kilojoules in the same per mole of organic matter. So microbial access to these electron acceptors controls the free energy, or the delta G, and that's the decay rates of our soils. So how can we predict microbial access, which is controlling respiration? First, our soils are built on carbon. So there's all kinds of compounds that are available down there for microbes to eat. So what we've learned from terrestrial ecosystems over the last 10 years is that the supply rate of electron acceptors controls access to free energy. Advection, physical transport, moves oxygen much faster, 10,000 times faster than diffusion, which is random Brownian motion. This diagram on the left is showing how this works in uplands, where mineral-associated soil carbon is slow to be exposed to oxygen compared to any organic carbon in the pore space. For our saturated wetlands, that advection is controlled by water in surface soils. And if you have advection of water in surface soils, that leads to high decomposition where oxygen infiltrates, but microbes in the deep, wet, stagnant soils can't access oxygen quickly enough. So they end up using all their oxidants, and they eventually end up with methanogenesis as the only way to get energy. The second key paradigm that came out of terrestrial literature is that, you can see that on the right, is that we have to get away from thinking about carbon quality as a classifiable thing. Rather, the decay potential of any carbon compound is a function of nominal oxidation state of carbon for any given electron acceptor. So for example, the ability of tannins or cellulose or carbohydrates or lipids or lignins to be oxidized with any one of the electron acceptors, that's what controls the free energy result, and thus the rate of microbial energy. And this scale of NOSC we can talk about later if anybody's really interested. So think about this practically. It's a simple conceptual model, but our wetland soils and sediments are chock full of carbon, and there's all of these compounds produced on site that are being deposited. What's mostly controlling whether they're eaten by a microbe or sequestered is the refreshment rate of oxidants. What is controlling the transport of fresh electron acceptors into the soil is primarily water. And so on this graph, you can see carbon preservation on the y-axis here, and then it's greatest in the red region where methane is produced, which is the low free energy yield zone. And that is a function of, again, no to low refreshment of oxidants. And then carbon preservation declines as we increase the supply of oxidants like sulfate, which happens with advective flows and air and water. And then when we get to aerobic respiration, we have high photosynthesis and such, and high respiration, but very little carbon storage. And we're going to look at this again in a second, but in the meantime, let's just look at how soils self-structure that way. Whether our soils experience advective or diffusive flows is based on their position relative to the surface, where the rhizosphere is, and then also the water table below, which is effectively sea level at any point in time for a tidally connected system. Healthy wetlands build their soils at the same rate as sea level rise by accumulation of organic matter and sediments. the fresh organic matter at the surface has a lot of advective movement of water moving, allowing for rapid decay, and there's a resulting compaction of that. And as more gets compacted, less fibrous, become more mucky, water moves through more slowly with low porosity and twisted pathways, and then the refreshment rates are much slower in those saturated soils. So that compaction actually limits decay, and eventually there's stabilization because there's virtually no decay, and actually there's no compaction at depth because water doesn't compact, you might remember. So sea level rise is keeping these older layers deeper, and it's getting more and more burial so that there's less and less access to oxidants. This means that, one, even though there's a lot of carbon down there, water flow, Darcy's law of groundwater flow, is probably the ultimate control on microbial access to free energy. And two, natural tidal wetlands have created their own vertical structure. Nature has developed this optimal system for carbon burial, and this is what I think we should be mimicking. So if we think about wetlands building their own vertical structure, we've got plant-driven expansion of roots making macropores and physically transpiring water. And so we've got all this advective flow that's dominating the surface and that provides for rapid microbial decomposition at the top. And then deep in the soil below the rhizosphere, we've got more stagnant water. And ultimately below that, we have because water doesn't compact, the soil matrix stays fixed, and oxidants primarily are refreshed only by diffusion. So again, 10,000 times slower. And so for an organic molecule to escape getting eaten or oxidized, the best bet is to get down to that bottom fast. And that's why there's so much literature now that shows that burial rates control carbon sequestration, that rates of sea level rise drive burial, and that primary productivity actually increases respiration rather than offsetting it. So of course, the data to show this kind of thing is very hard to get, but I want to highlight that before I began this detail with the Delta Stewardship Council, colleagues and I at the Department of Energy and Yale University have been working on testable hypotheses about soil structure and age and carbon preservation and iron. And while the data are still forthcoming, we can say that deeper soils at Rush Ranch, here on the left in Suisun Bay, are less porous and have a higher tortuosity of pores. If you go deeper, you'll see more tortuosity, lower porosity than at the surface, which is more porous and less tortuous, less twisted. The more we understand the matrix of where we are trying to store carbon, the better that we can understand how how that matrix is changing with time, whether it's natural or managed drivers, and the better we can quantify its potential to stabilize carbon. So again, why this deep dive into first principles? Going to close by highlighting that it helps us prioritize what we're doing. It also tells us the physical limits of our ability to hack the system and avoid trade-offs. There will always be trade-offs. Any increase in oxidant respiration by adding gypsum, calcium sulfate, or iron or nitrate to the system, it might initially suppress methane emissions, but once those oxidants are reduced, then the effect is gone and you have to keep adding them. And there's long-term effects of things like sulfides on plants and animals. To maximize soil carbon accumulation but suppress methane emissions, the only other way is to make sure that any methane that is produced is oxidized on its way out. So a oxidized water column above our sites can help do that. Tidal connectivity hits all the buttons for the right hydrology. Q can be high at the surface with tidal exchange, and then Q can be low below the water table so that you can stabilize carbon at depth. And then for sites that aren't connected to tides yet, again, if you can try to mimic this, we might have our best results. The other good thing about Q is that it's monitorable and it's modelable with elevation, porosity, and tide gauges. And I'm going to argue that our best approach will always be to focus on holistic ecosystem restoration, not these short-lived interventions like hacking the system. Natural processes are resilient, and frankly, we don't have to hack the system. We have some of the highest densities and the highest rates of carbon sequestration in the world. So I think we should lean into that strength. There's huge wedges of opportunities across the estuary. And We can talk about different examples. Sassoon, I'm just highlighting here as being one where methane, we're actually having significant carbon preservation with low methane emissions because of the particular salinity and the tidal connectivity. In the deeply subsided delta, we can't connect the lands to the tides yet, but again, we can think about protecting that carbon by controlling the hydrology. And I'm just going to end by talking about disconnection. It has costs. We're seeing it now in the loss of transgression opportunities for wetlands all over the estuary and the huge bowl of subsidence that's jeopardizing people here in the Delta and all of those that depend on Delta resources. If we move from boundary thinking to estuary thinking, we can gain all these benefits that we'd be missing if we just focused on maximizing carbon storage. And we really can't game the system anyway. The whole game should be ecosystem restoration and resilience, goalposts to help you think like an estuary, which are unique places where all on the landscape where everything comes together. Grant will talk a little bit more about the importance of connectivity, but I'll just close by saying connectivity, all kinds, is key to permanence and to multiple benefits. I'm going to make another point about connections being important to the resilience of the estuary, and also another elephant analogy that, people save what they love. Charismatic megafauna. We really need to communicate the power of this estuary and let people fall in love with the estuary and all that it does for us. People's love for the estuary is the superpower that we have not yet unleashed. And it's that contribution of estuaries that is just not being fully appreciated. They are huge reactors where everything's coming together to be bigger than the sum of its parts. There are lots of opportunities for carbon sequestration in the system, but there may be 1/100th of the importance of all this carbon moving around. And the value that's generated by that carbon. It's building elevation for resilience to sea level, which helps us mitigate floods. It's moving its way out into the ocean for long-term sequestration is alkalinity, which could potentially offset acidification. It's fueling food webs and birds and humans. Rebuilding that carbon pool is an opportunity for communities to be connected, particularly on agricultural lands where farmers of carbon need to get paid, which is critical to broad-scale adaptation of, or I said broad-scale adoption of wetland restoration on private lands. And I want to return to our need to be able to transition between quantifying carbon benefits between different units, solid, liquid, gas, different rates of fluxes and so on. It takes a community of practice to be able to build the skills to crosswalk those units and at large scales and communicate them so that everybody can see the whole estuary. And that community of practice is what we have today. You in the room and those of you online that are tuning in, I'm so happy to see that. We also have this amazing lineup of presenters and moderators who can lead us in a community discussion of where we are and where we need to go, next steps for scientists to help move forward the practice and policy of blue carbon. I put an image on of the new seamless estuary wide LiDAR behind here, because again, it's one of these tools that we have to start breaking down barriers between the components of the estuary. Bringing people together is what moves the needle, and I am so grateful to CMSI for and all of you here for being part of the conversation that we really need to have about this elephant in the room. So in the spirit of bringing people together, I leave you with this humorous perspective on carbon, and I hope we all can continue to work together here in this estuary. Thank you. I'm happy to take questions. In the last 2 minutes.
Thank you, Lisa Marie. That was really fantastic. Cam Blinger with Delta Conservancy. We have several large-scale managed wetland projects currently in design in the Delta. Do we have a way to model or optimize that, the hydrologic, the flow rates to minimize, to create that oxygenation and minimize the methane production?
Yeah, thanks, Campbell, for the question. I think all of those restorations are a fantastic experimental opportunity. And so I would hope that these groups are talking together, perhaps through the Delta Carbon team, to talk about changes between years, different decision points. I know that, for example, I just found out from David Julian yesterday, they're about to change the hydrology at Twitchell. And, you know, rather than worry, I think we should take advantage of that change because it probably will alter the water quality and then also the rate at which water is refreshed on the landscape. So I think I have some ideas of how you can model it in terms of just very basic hydrology and Piclet values, so advective versus diffusive flux, things that you can measure with chloride, things like that. But in general, we've got a lot of actions out there that could be monitored and shared of information so that we can start building these into models like Peppermint, which does have a water flow component. I saw Tomoko's hand.
Yeah. So Peter Goodwin with ISB. First of all, I think it's remarkable how much we've learned in the last 10 years. This field has really advanced. I was just curious, when you see those very large uncertainty values in things like density and everything else associated with this, is most of that uncertainty due to the heterogeneity at a single site, or is it big differences between different parts of the coast or different parts of the landscape that you pointed out?
Yeah, thank you for the question, Peter. The variability is real, so it's not, I don't think a lot of it is measurement error, but we need to get better at not just taking syntheses of all that variability and then reporting it, but actually modeling out where, you know, what's responsible for their variability so we can remove some biases and have a more representative data set. So the variability is not typically measurement error in the terms that I'm showing, but in the true variability of the system, because there is pieces that are, you know, that are very different from each other. So actually exploring uncertainty is another really great topic for us to do today and then in this Delta Carbon team. Thanks for the question.
Well, I think it's time for a short break. So we have 15 minutes before the start of the next panel if anyone wants to use the restroom, refill coffee, or anything else. We'll reconvene at 10:15.
All right. So I'm Chris Jancek. I'm research faculty at Oregon State University. Worked on blue carbon. I'm excited to be here. There's always so many aspects of blue carbon that you learn something new in a symposium like this. Our first speaker is Stephen Devereaux. He's with HydroFocus. He used to be with the USGS, and he has a PhD from UC Davis. I'm going to keep these introductions brief, but Stephen's going to talk to us about some work in the Delta.
Thank you, Chris. Good morning, everybody. Appreciate the opportunity to speak here today. I'm going to delve into the issues in the Sacramento-San Joaquin Delta and the reversal of subsidence in this talk. I'll give some background first and then dive into 3 projects we've been working on that really represent this interdisciplinary assessment of alternate land uses in the Delta. I would acknowledge my co-authors and cooperators here in this work that we've been doing. HydroFocus employees, Savannah Haas, Nick Christian, Greg Aiken are here this morning. Sabina Dore, Mark Olds are not here, but they've been instrumental in a lot of this work, as have other people, as I'll mention as I move forward. So really, as I mentioned, the subsidence issue is really the driving force, in my opinion, for this modification or creation of alternate land uses in the Delta. And you get a sense of that here looking at this picture if you haven't been out there. If you go out to Staten, you'll see a similar situation where standing on Twitchell Island here about 20 feet below sea level, you look up at the San Joaquin River channel and you see a boat going by that's above your head. It gives you an idea what subsidence is like in the Delta if you haven't seen that. when I was a graduate student here at Davis, we had a meeting on a subsided island that looked about like this. And one of the professors that had come from Arizona, University of Arizona, said, "What the hell are you guys doing out here?" And that's a good question. You know, back in the early 80s, nobody was really thinking about this too much, but we've since gained some consciousness around the subsidence issue in the Delta. And it's really the result of this decomposition of the peat that accumulated during the last 6,000 years in the Delta. We accumulated about 8 billion cubic meters of peat during this tidal accretion process and sea level rise. And since the mid-1980s, we've lost about 2/3 of that peat in the Delta. Because of the drainage of the soil, we oxidize it, we release CO2, and so there's a large carbon dioxide emissions associated with this subsidence. So they're really intertwined, the carbon dioxide emissions and the subsidence. And though the consequences are fairly serious, levee failures have been one of the most serious ones. This shows the 2004 levee failure on Jones Track, which was the last major levee failure in the Delta. But before that, since the 1950s, we've had over 80 levee failures and island flooding in the Delta. And there's an issue related to seepage, which I'll talk more about, which is a problem for levee stability in the Delta. The other consequences are it's getting harder to farm out there. As the soil gets wet, the tractors can't move, they get stuck, the farmers stop farming that land. We estimated in a paper in 2015 that the area of non-farmable land in the Delta had increased tenfold from 1983 to 2012, and it's increased more since then. So it's a substantial problem with subsidence just from a farming standpoint. But I wanted to follow up on this seepage issue because this is a graph that we published in 2012. I'd like to acknowledge Sandra Bouchon's work on this. She was one of our co-authors. And really what it amounts to has to do with this exponential curve that you see relative to marsh deposit thickness. Doesn't look like the numbers got transferred here. But anyway, the relative probability of failure increases exponentially as that marsh deposit thickness decreases. So what that means is that there's much more underseepage under the levee that can erode levee foundation materials. And what that results in is this. So it's basically these sand boils that can occur. And this was one that I took a picture of back in 2011 after the Jones Track failure on Jones Track. Underseepage was a causative factor of the Jones Track failure, and we still see these on islands and are doing some work to try to quantify where these occurred and where there is greater underseepage potential. But basically what you have now is a hydraulic force under that levee, and as the tidal marsh has disappeared, you don't have that blanket that protects that land side, and you have this levee foundation material that erodes, that can cause levee failure, as did happen on Victoria Island in 2024. There was a huge almost levee failure on this island. It was due to underseepage, water eroding sand and sand layers underneath the levee and flowing out onto the island. 5,000 to 6,000 gallons per minute of sediment-laden water moving onto the island. They were able to stop it by putting sheet piles in and stopping that underseepage. So in answer to that, one of the things we started working on at the USGS in the early 90s was examining subsidence and ways to reverse it and stop it. And this is the first really pilot project example, the first wetland in the Delta that was created in 1997 with cooperation with DWR, Kurt Schmoody was a big part of this. And since then, there's been a lot of work done. And I acknowledge in particular the Baldacci Lab at UC Berkeley for doing a lot of the work relative to eddy covariance and quantifying basically the carbon balance of these wetlands. So we've seen about 3 centimeters a year of accretion at this wetland from 2007 to 2017. Want to acknowledge also that you see the amount of biomass that's accumulated out there, and we know that these managed wetlands really are a way to look at how that thatch that accumulates inhibits an acid vegetation, and looking at ways to manage that in a better way. So I want to transition to Staten Island, which is really a learning laboratory for trying to look at this interdisciplinary process of trying to find alternate land uses for these subsided islands. I want to acknowledge the Nature Conservancy for getting Hydro Focus involved in this back in 2011. We've worked with many folks at TNC to try to understand how basically the Staten Island can become a more sustainable situation. It's in the middle of the delta, as I talked about earlier. Churchill Island is in the west there. Staten Island is towards the more center of the delta and has a variation in land surface elevations. We wrote a report in 2012 where we tried to look at factors affecting sustainability on Staten Island and alternate land uses. And what we found was that there was a potential for future levee instability. We suggested rice as an alternative. We'd done work on Twitchell Island before this, demonstrating that rice can stop subsidence. And it really was the beginning of the mosaic concept, which is based on subsidence rates for Staten Island. Really, at that time, we estimated subsidence from the early 1900s, 2007, which is the first LIDAR flight. And you can see the variation in subsidence during that time on the island, where it was fairly low, either in feet, 2.3 feet in the northern part of the island. There are less organic soils, but as you transition to the southern part of the island, you have much higher subsidence over time. So this really set the stage for creating a different mosaic of land uses that was the case at the time, which was mainly corn for the island. There were some potatoes, pasture, and alfalfa, and grain crops as well. But what we transitioned to and what we looked at in a paper we published in 2017, which with the Nature Conservancy and Rod Kelsey and Paul Jacobs were part of that, we looked at the possibility of this transition to creating rice and wetland in the southern part of the island, where the subsidence rates were the highest and the greatest possibility for subsidence that could cause levee problems in the future. This is one of the scenarios in which we had rice and wetland. There's about 1,000 acres of wetland in the southern part of the island. And we found that there was definitely a reduction in greenhouse gas emissions. There was a slight decrease in revenue, and there was potential for even greater revenue if we converted where the wetland is slated to be here to rice. And so this prompted, I want to say that we were the cause of it, but there were some other causal factors too. But I remember Witold Zielecki, who was really instrumental in getting this work started on Staten Island, said he wanted to prove Deverell wrong. But it turned out they planted rice and moved forward with that in 2019, about 300 acres. And since then, we've done more work on Staten Island, actually quantifying that greenhouse gas emissions reductions using eddy covariance towers in the corn and the rice fields. And we've also worked on measuring the land surface elevation changes associated with rice using sedimentation erosion table. You can see how the groundwater elevations change over time as it's drained for planting and harvesting in the spring and the fall. But the upper graph, the colored graph, shows this general stopping of the subsidence and possibly an increase in land surface elevation over time. But to note the fluctuation in the land surface elevation with groundwater elevations is important because it kind of plays into what Lisa Marie was talking about. And, these peat soils can be lifted up by the groundwater fluctuations. And this is our sedimentation erosion table at the rice field. And we've also used modeling to quantify the spatial variability on Staten Island and other places. It's a simple subcalc model, estimates the greenhouse gas emissions associated with subsidence as well as estimating the actual subsidence. And it uses the Michaelis-Menten and subsidence kinetics. As it's shown here, we've been able to calibrate it with eddy covariance data throughout the delta. And so it serves as a tool to estimate what the overall benefit in terms of emissions reductions is. So this is the current land use. After 300 acres in 2019, they increased the acreage to 4,600 acres today on Staten Island, and we're planning a wetland in the southeastern part of the island of about 1,000 acres. We have done, this is a more experiential approach that we're getting ready to publish this year, which speaks to the estimated greenhouse gas emissions reduction of 21% relative to the baseline, which is that corn for most of the island. Reduce soil life by 75% over 50 years. And actually the estimated net revenue is 2 million greater than for the island, for this 9,300 acre island than the baseline. We've worked with UC Merced on doing the modeling and the economics. And we've also worked with TNC and Point Blue to quantify the avian benefits of these conversions. And so you can kind of see the resemblance there of the original mosaic concept based on the subsidence on Staten Island and how that current mosaic corresponds to that. So this mosaic concept has been extended to the Metropolitan Water District islands. We've worked with California Department of Fish and Wildlife funding and Metropolitan Water District, in particular, Russ Ryan has been really instrumental in moving this forward. We started with looking at all 4 islands and moved to more specific scenarios with Bolden Island, and now WebTract is moving forward well. It's really been a transdisciplinary, interdisciplinary science project where we've worked with Brett Milligan at UC Davis, here at UC Davis he's in the Human Ecology Department. And so there's been structured decision making as part of that, using stakeholders and a technical advisory committee and indigenous input as well. So we've tried to basically have a collaborative assessment of adaptations, look at what the business as usual greenhouse gas emissions are, subsidence rates, potential for levee failure, and selecting the island that would be used for a more detailed scenario. Bolden Island ended up being that island for a number of different reasons. So this iterative process of collaboration and developing scenarios and using the science to quantify subsidence, mitigation, greenhouse gas emissions reductions, ecological habitat, and revenue has been part of that interdisciplinary and transdisciplinary process. So this is what we've come up with. This is still in the planning and design phase, but you can see the different adaptations here, similar to what we did on Staten Island. Much of the island, 50% of the island, it was slated for rice, but there are tidal wetlands planned, floating wetlands, non-tidal wetlands. Floating wetlands are kind of a new concept that we've worked with a little bit. We published a paper on that in 2024. But the bottom line is that there's this volume, net soil volume increase relative to baseline of about 439,000 cubic meters on an annual basis, and a estimated greenhouse gas reduction of 75% relative to baseline. So there's a substantial benefit not only from a greenhouse gas and subsidence reversal benefit, but the placement of non-tidal wetlands around the edge of the island, and the rice can also alleviate this under seepage problem that I talked about earlier. So moving on to WebTrack, I wanted to acknowledge a number of people that have worked on this project, and in particular, Melinda Stalvey has really led the charge on this and getting this project actually ready for implementation. Construction will probably happen this year. We're at 100% design. And it's a similar mosaic that we have this wetland on the western side of the island, we see here with the blue, but it's also an area that was too wet to farm. And so that's one place where we see emissions reductions, even though it hasn't been farmed for several years. There were substantial baseline emissions, and the gray area is the rice, proposed for rice. The wetland and upland habitat of 2,900 acres will not only provide substantial habitat, but also provide halt and reverse subsidence, reduce greenhouse gas emissions, provide food web benefits. It's something we're going to explore, and explore polluted culture opportunities, which is really the economic use of wetland vegetation. And we are doing greenhouse gas measurements. Baseline, we've completed over a year of baseline measurements and have been able to estimate what those greenhouse gas emissions reductions will be using the combination of the eddy covariance as well as our subcalc model. And the bottom line is about 28,000 tons of CO2 equivalent per year, which can result in an income that's commensurate with lease values in the Central Delta at this point. And the other thing about this project is really inspiring, I think. We had ecocultural involvement in the Bolden Island project, but not as extensive as in this project. And it's really been helpful, I think, to have that involvement and use that applied ecocultural restoration framework for delineated areas in these sand dunes that have appeared as the peat has disappeared. And these were areas where there was have a ceremonial value for the indigenous folks. So this was part of the process. So I would just in closing say that I think the work we've done in terms of this interdisciplinary analysis, which is really the key, I think, transdisciplinary and interdisciplinary, has really demonstrated that there are potentials for alternate land uses in the Delta that can not only provide greenhouse gas emissions reductions, but also increase sustainability with the threat of subsidence over time. Thank you.
Questions. The three talks in this session will go and then have questions for all the speakers.
Okay, our next speaker is Tyler Anthony. He's a senior environmental scientist with the Department of Water Resources here in California. He's going to continue discussing blue carbon in the Delta. And Tyler was previously at UC Berkeley, where he did a PhD and postdoc on blue carbon.
Yeah, thank you very much. Thank you all for being here today. We're really excited to follow Lisa, Marie, and Steve. It's hard talks to follow, but I am a geochemist by training, but at DWR, I'm our carbon sequestration and greenhouse gas emissions reduction specialist, and so I'm really trying to take that work and kind of apply it both from a policy lens, but also as just a lens on how do we scale and meet some of the goals that we have as a state here in the Delta. And so just quickly, I'll try to go through background. We've already gotten plenty of good background this morning, and then kind of dive into actually what we're doing with carbon credits, a little bit of the lessons learned from a lot of these long-term data sets that have been discussed already, and then where I think some of these next steps should be going. But also would love to have feedback and talk about that all later too. But really just again, that the current Delta trajectory, that we have economic threats from subsidence, increasing costs from levee and drainage. We have salinity, increasing soil and water management costs, both from saltwater intrusion and just extended periods of drought. From a climate perspective, these drain peat soils are some of the most significant greenhouse gas sources anywhere on Earth. So I won't actually talk too much about nitrous oxide today, but it is up to 10 times more nitrous oxide per acre than conventional corn agriculture. So some of the highest nitrous oxide emissions we measured anywhere on Earth were here in the Delta on Bolden. On top of some of the highest carbon dioxide emissions anywhere on Earth. So really, this is just a significant greenhouse gas source, right? 1.2 million tons of CO2e per acre per year. And then this subsidence and relative sea level rise are exacerbating this flood vulnerability. And both the flood occurrence and then recovery from that is expensive, both at the local level, but also from the statewide level, depending on its impacts to our water supply. And so really from a DWR perspective, these deepening islands are risking levee failure and salinity risk, particularly on Sherman and Twitchell. Those are integral to the water quality through the Delta. And then this is all further worsened by drought and sea level rise and potential further saltwater intrusion. And so potential land uses need to be further explored. And there's just plenty of related California legislation around this. And so we have multiple goals of reducing our emissions by 40% or more by 2030, and then carbon neutrality as a state by 2045, and that includes land-based emissions. And then from a state agency perspective, DWR actually has to be net zero by 2035. And so these timelines, that's 9 years away. We need to keep moving in this space. And so AB 1757 is a great tool that California has used to really help set these nature-based solutions targets for 2030, 2038, and 2045 to both sequester carbon and reduce emissions from our land uses here in the state. And is a key part of this net carbon neutrality goal. And so that includes conserving and restoring 12,200 wetland acres per year through 2045. That is 280,000 acres. That is a big goal that we need to accomplish. And just in the Delta, we have similar goals for the Delta Ecosystem Plan Amendment for somewhere around 60,000 acres by 2045. We are not on track for that goal. So we need to figure out ways to start scaling these things and find other ways to fund it. State funding is a key tool to this, but it can't be the only tool to reach these goals. And so much we've already talked about today as DWR supported research is why we're here. We have over 25 years of observations. We have gold standard data sets. And we really know that these solutions both reduce greenhouse gas emissions and sequester carbon. And so there's both this baseline reduction, but also net sequestration that we really need to highlight and really sell as a tool. This is one of the best nature-based climate solutions we have from restoring wetlands. And all this work has really allowed for carbon market development, but how do we scale that carbon market development and really deploy it today? So that's what I'll try to talk about from DWR's perspective. And so why leverage carbon markets? Again, that brings capital beyond state budgets. So yes, wetland restoration is a state priority, but there's not enough funding to go around for all the projects we need to do. It helps create incentives for landowners to consider changing their land uses to more sustainable and more climate benefit approaches by monetizing greenhouse gas benefits. So that's the tool. It might help cover upfront costs, or at the very least should cover management costs from a state agency perspective. and then can develop a durable ongoing revenue stream instead of having agencies depend on general funds to maintain these wetlands over long time periods. And it all does this all by helping meet our statewide resilience goals, and then also potentially giving tools for smaller scale community focused restoration feasible. To make that feasible, I'll try to talk a little bit about some blossoming ideas around that, and hopefully that might gain a little bit of traction. And so there's many different versions of carbon credits. So thinking about carbon credits in this aspect today is through American Carbon Registry emissions reduction credits. So there is a California-wide wetland restoration methodology in the American Carbon Registry that we have used at DWR to generate carbon credits. And these are really just verified reductions in greenhouse gas emissions. So that kind of encapsulates both net carbon sequestration and just reduction in emissions relative to some baseline. And so it's kind of two kinds of credits all kind of wrapped in one. And then organizations can use these credits as offsets to get to their net zero goals on the voluntary carbon market. And because of the multiple co-benefits we've already talked about today, we do think that these Bay Delta specific credits are likely valued over $30 a credit. But we still need a buyer. So we could say they're worth something, but until we sell them, that's all hypothetical. And just a little bit more of reiterating why Delta wetlands make high value credits is that they stop significant emissions. Long-term hydrology and management, particularly in the Delta, really support durability of these systems relative to other nature-based solutions. They face low reversal risk. It's really hard to set them on fire or lose them in other ways and re-emit that carbon to the atmosphere as long as you maintain that hydrology. And it's fairly easy actually to monitor these carbon outcomes with water and soil indicators as long as we have the right tools and models available to us. And I think we do, particularly here in the Delta, because of this extensive scientific research. And so we have credible, verifiable, and scalable accounting. But it's not quite being scaled yet. At least at DWR, we are showing that we can generate carbon credits at a scale of thousands of acres. And so we have about 3,300 acres in our American Carbon Registry project and are very close to getting 112,000 total carbon credits. We have 52,000 credits already verified. We're waiting for our next round of verification on another 60,000. And they are generating credits at a rate of about 10,000 credits annually. And we hope to have on Sherman and Twitchell about 45,000 credits a year by 2050, or at least the net emissions reduction amount by that. So one credit is 1 ton of CO2e, just as to convert to what we've been talking about earlier today. And so it's about $3.4 million today, and then $300K to $1.5 million a year moving forward into the future. And so really we're trying to explore the sale of these credits at DWR to really help offset some of the long-term management costs so that we don't have to compete for general funds to maintain these state assets. But really the value of these credits are uncertain. If you don't actually have any supply or demand, you can't know what their true value is. And so we're really trying to explore what does selling look like at a state agency. State agencies have their own unique characteristics and regulations and authorities that they need to really get in line to sell these things. And so trying to line that all up. And I think there's some positive movement behind the scenes. But that's all we can really say at this point. But really trying to actively sell them. And so if you can find us a buyer, that's also another way to kind of get this thing moving. If we have pressure for this money, we need to get money, we can make things move a little faster. But some of these hurdles to scaling are really that DWR is the only entity capable of selling these credits right now. Nobody else has wetland-based carbon credits in the system. And so if we haven't sold any, there's no value determined, or again, that's uncertain. And then we have heard from CARB in this space that any consideration of this methodology in the compliance market really depends on voluntary market demand. We need to show that there is some supply and demand in the voluntary market to get adopted into the compliance market. But we have seen that and expect that we can get similar values per ton on the voluntary market, so that might not be necessary. But we do need to sell them to really know what these true values are. And there are baseline concerns that need appropriate responses. We know that the delta is a mosaic of land uses, and that's a mosaic of greenhouse gas emissions. And we want to make sure that we can establish fair, equitable baseline estimations so that we have true greenhouse gas emissions and we don't have greenhouse gas emissions reductions, but we also are not gaming the system and making sure that it's done in an equitable manner. And then some of those solutions that we're really trying to work on with many of the folks in the room today are trying to scale monitoring. And so we have long-term data sets that are high quality, state of the art, that we can blend with models and remote sensing to potentially lower costs. There are still several site-specific variables that we maybe need to constrain a little bit, but that might be solved with things like mobile towers or using these like regional climate and carbon analytics tool coming out of UC Santa Cruz and LBL to kind of start to think about how we accurately scale these estimates across the delta, both from conventional land uses and from restored ecosystems, so that we can have a centralized, consistent accounting method. And that really leads into the next one. Another potential solution is trying to centralize this carbon accounting method. Some of the difficulties both with scaling carbon credits is there's many different ways to measure carbon and quantify carbon in the delta. And so that makes a lot of confusion in our messaging potentially, and potentially centralizing how we account for it and where we're accounting for it can really streamline that messaging to both reduce, just improve our messaging out to the broader public about the benefits of these systems, but also can potentially reduce technical and cost barriers for entry. And so DWR is very lucky to have a biogeochemist on staff that can help them with carbon credits, but a 50-acre farmer cannot enter into this market without some centralized accounting system where they can go and have a lot of those technical and cost barriers kind of handled for them. And then it really helps lower overhead costs. So we can potentially make our verification costs work at the scale that we're at DWR, but not everybody can afford a $30,000 verification every 5 years and continue to generate credits and revenue above that. And so this might help improve transparency and also improve facilitating climate investments to reach those higher risk underserved communities and really expand access across landowners in the Delta, as 80% of the Delta is privately owned. And so since I'm a scientist, I did want to talk a little bit about some of the science lessons that we've learned, because it is really exciting just being able to work with these data sets every day and just continue to learn from these long-term data sets. Really not well represented by this graph, but we are seeing that net removals are an increasing proportion of our credits. That's because methane emissions are going down over time. And so these are just two examples here of Mayberry and West Pond. So two DWR wetlands. Mayberry is on Sherman, and West Pond is the original wetland that Steve was just talking about earlier. And you could just see darker lines just mean older wetlands. And so, and just looking on the far right on the x-axis, that's the end of the year. So whatever the total amount of emissions of methane at the end of the year. And you can just see that darker lines are lower than the lighter lines. And so methane emissions are going down. And so really methane might not be so bad. But there's also ways, I think, that we can start to try to use theory. So Lisa Marie had some great graphs there on trying to reduce methane emissions. Can we kind of sit between that red and yellow line that she showed in her carbon preservation graph to try to maximize our carbon preservation, but try to minimize our methane emissions? I think there's a lot of leverage in near-term climate solutions to lower our methane emissions, but there's also a lot of bang for your buck, I think, because it's these ecosystems emit so much methane that reducing that methane just a little bit just gets us several more carbon credits, but also is just a better climate solution. But we need to really test those things and test those things at scale. And so trying to think about that a little bit in these systems. And really, we know that plant establishment is necessary. So just at the top, we have Hill Slough and Sherman wetland. that didn't quite have the same rates of revegetation following restoration as some of the other islands. And really in the beginning, they were actually net sources of carbon. So this is cumulative net ecosystem exchange. And so just any positive value is a CO2 source and any negative value is a CO2 sink. And you can see these two sites that had poor plant establishment were really just net sources still because they didn't have plants sequestering carbon through photosynthesis. But in places like Gilbert Tracts, so that's Dutch Slough, it was pre-planted, and in its first year of restoration, it was a significant carbon sink. And so we can really start to jumpstart this carbon sequestration potentially by pre-planting. And it also had much lower methane emissions, but understanding whether or not that was tidal connection or some combo of pre-planting and tidal connection is a question. But still, there are pre-planting CO2 effects almost immediately. And really, there is that still question of the lateral fluxes need to be constrained, but DWR, most of our wetlands are impounded wetlands. So we do want to know from like Dutch Slough's example of what the fate of that lateral flux is and how that should be accounted for in carbon accounting. But still, it's removing CO2 from the atmosphere in the near term. And in these impounded wetlands, we have very good data showing that the eddy covariance measurements, so those are net atmospheric carbon uptake here in blue on these graphs. And then the tidal, so Eden is in the bay proper, and the non-tidal managed is Mayberry on Sherman, and then non-tidal managed. The other one is East End on Twitchell. And you can really see in Mayberry and Twitchell that the net carbon uptake in blue is almost equal to measured soil carbon accumulation uptake in red. And so the carbon that we're measuring being carbon uptake we're measuring in these systems is staying as soil carbon in these impounded marshes. And so there isn't really a lateral carbon flux concern as much in these systems. We know that CO2 is being kept in those systems. But it really is in managed impounded systems. And so how do we deal with tidal marshes versus these impounded wetlands in these carbon markets? And quantifying the true balance is something to consider. Oh. Sorry about that. Siri likes to tell me about carbon, I guess. Yeah. And just one last one, Steve touched on it a little bit with this excess thatch that we really are seeing in some of these wetlands. So West Pond is, close to 25 years old, if not more. And then other places on Mayberry and East End are 15 plus years old. And there's just this accumulation of plant material on the surface. And this dead above ground biomass is actually shortening the growing season. And so it's sort of easy to see in this uptake length in days on the left-hand side. And so West Pond is just an older wetland. And so the number of days, even though it's directly next to East End or surrounded by East End wetland, it just has a shorter growing season because this excess biomass is lowering soil temperatures by insulating it in the spring. And so your onset of spring is later than in East End. And so you just have less days that you're growing plants. And so you're going to have actually lower net ecosystem exchange. And so thinking about managing that biomass to try to increase this uptake length might help us improve our carbon sequestration ability even more in these systems. And so it's not just restoring and walking away, it's actively managing to try to maximize some of these results. And so just quickly, some of these next steps is how do we improve this biomass management? So we do see that it might be reducing sequestration, and so we want to see if that's actually true. If we remove this biomass, can we kind of improve rates of sequestration? But it also has a lower habitat value than some of these mosaic tidal wetlands. And so removing this excess biomass might help improve this habitat value, and actively managing it might maintain that over time. And this may also be slowing soil accretion. So how do we complement this biomass management with improved soil accretion measurements? So some potential measurements are cultural burning to try to remove this biomass, and really working with ecocultural practitioners to manage these systems the way they were managed prior to contact. But there's also other methods like Marshmaster mowing. Marshmaster is just a floating tractor that might be able to help just push this material under the water and help improve space for new growth. And then also polluticulture and harvesting is something we do need to explore, and we need to explore it at scale to really see if it has any potential. And so, but hopefully just quickly that their key takeaways from this is that the methodology for carbon credits is proven, but we really need to work on scaling it. And we should work on thinking about how we can better manage for biomass and methane emissions that might have significant trade-offs just for active management. But we really need to scale. Current projects will not meet these targets that we've set for ourselves as a state. And there are many uncertainties and spatial heterogeneity, but that should not hinder access. And lastly, we are trying to sell credits, so any active help is always helpful. And couldn't have done it without the many organizations helping us through all this work. So thank you very much.
Thanks, Tyler. Our final speaker for this morning session will be Grant Gutierrez. He is an applied environmental anthropologist and political ecologist who works at Carbon Direct, and he's coming to us from the state of Washington.
Hello, everyone. Good morning. My name is Grant Gutierrez, and I'm the head of community impacts at Carbon Direct, and I'm also the affiliate faculty at University of Washington School of Environmental and Forest Sciences. I'm really glad to be here today and join you all, and thank you to the symposium organizers, Alyssa, Moose, Brooke, who invited me, and others for extending the invitation. I've already learned so much in preparing for this talk, and listening to Lisa Marie and Steve this morning has been very instructive as well, and I'm looking forward to being in conversation with you throughout the rest of the day as well. Just a bit of an introduction of myself, as I'm an outsider to the system and don't work in the Delta. I'm a political ecologist and cultural anthropologist by training, and my work broadly addresses the environmental justice dimensions of ecological restoration as a form of climate change adaptation. And I've conducted community-based research in southern Chile around hydropower development and watershed conservation, and in the Puget Sound region, where I live and work now, on floodplain restoration and Superfund pollution remediation. At Carbon Direct, I lead the community impacts team. And so Carbon Direct is a climate science advisory firm that really has a core business function to support the development and delivery of high-quality carbon removal projects. And my team is responsible for the social science and environmental justice advisory work across the firm's business, including things like community engagement, community benefits, and other dimensions. So my talk today is titled Permanence is Political: Community Co-Benefits and the Durability of Carbon Storage. And my hope is to invite us all to think through the social determinants of permanence and draw on some case studies from my work at Carbon Direct, doing community benefits co-design, to really illustrate how carbon projects in different systems are thinking about and implementing community benefits to increase durability. Great. My talk is organized into 3 sections over 14 slides. In the first, I want to unpack some of the great social science research that really exists in the Delta system, namely the Delta Resident Survey, the Tribal and Environmental Justice Framework, and also the Delta Governance paper from the Forest Service, to really highlight some of the complex social landscape dynamics that exist in the Delta. In the second part, I'll briefly review 2 different carbon projects that Carbon Direct supports through our community benefits practice, one in Louisiana and one in the state of Amazonas in northern Brazil, and then discuss how these projects are working to ensure community benefits to advance both carbon permanence as well as equitable carbon projects. And then the last section, I'll just briefly wrap up and end with a question. So when we talk about carbon permanence in carbon systems, I find the field tends to really frame the challenge as a biophysical one. In the Delta, those are biophysical dynamics like soil subsidence, methane flux, salinity threshold sediment dynamics, things that you all know much better than I do. And these are real constraints that exist in these systems. But I also want to suggest that perhaps another wicked variable in risk to carbon permanence in all systems, and especially in the Delta, isn't just biological, it's political. It's the human and social relationships that shape how we implement scientific management decisions, how we develop systems of care that endure through the generations. And the quote on the right here comes from the 2023 survey, the Delta Resident Survey of more than 2,200 Delta residents, and the largest study of its kind in the region. And I really liked reading this survey. I think it's excellent. And someone in the survey was asked to describe the Delta, and they said, "It's a beautiful place to live, full of life, trees, plants, and animals. The land is rich and a great place to grow food. The waterways are fun to play in. And if we are responsible, we will have it for many years to come." And I keep coming back to that phrase, "if we are responsible." And to me, that's not just an ecological responsibility, but a social and a relational one. So the thesis that I'm making today is that the biophysical permanence and social permanence are intimately intertwined, that the durability of carbon storage is a complex, contested landscape like the Delta depends not just on the science, it depends on the quality of community relationships with restoration projects. So said in a different way, a blue carbon project is a 40-year relationship. And like any 40-year relationship, it lives or dies on trust, shared power, and whether people have a real stake in the outcomes. So just to kind of unpack some of this, Rudnick et al. In their Forest Service paper in 2025 really did a look at the governance system in the Delta and found over 300 actors operating in the Delta water management system. That's 300 distinct entities, federal agencies, state agencies, water district, tribal nations, agricultural interests, environmental and community groups, each with some stake in how water moves through the landscape. And that's kind of what we would call polycentric governance in practice, complex, fragmented, and sometimes slow to coordinate. And as we kind of learned from Lisa Marie today, and as I was reviewing her work, her 2023 paper, modeling carbon projects across the Delta over a 40-year time horizon, one of the variables that the paper argues the single largest source of uncertainty in these models was flow and water operations. And that really stood out to me, especially as someone that works in watershed management, that ultimately long-term permanence is shaped by biophysical dynamics of hydrology, but that's also a political decision, and it's also a governance variable. And so that means that already in the system, permanence is political. Permanence is being shaped by these political decisions that exist over the long term. And as a social scientist, I tend to think of politics as an interconnected and multi-scalar set of social relationships. A lot of social scientists that work and study the state as an entity will call this the relational theory of the state. So what does the community landscape in the Delta actually look like through an environmental justice lens? So the Delta Stewardship Council's environmental justice issue paper really gives us a useful three-part framework that draws on kind of the broader environmental justice scholarship. There's representational justice, so who has a seat at the table? There's procedural justice. Is the process in engaging stakeholders fair, equitable, and transparent, reaching the right people? And there's distributive justice, which is really kind of the core of community co-benefits. Who bears the burden and who receives the benefits? And these aren't just abstract categories. They can be diagnostic for every project that operates in this landscape. So when I reviewed, again, the Delta Resident Survey, I found a really important insight that should probably resonate with everyone in this room. The Delta Resident Survey found that residents trust scientific experts and community advisory groups much more significantly than policymakers at any level of government. Federal, state, and local, all of them are significantly less trusted than scientists as independent experts, and potentially our scientists are seen as fellow community members. So your credibility as scientists and practitioners with Delta community members is really real. And this is a real opportunity for using our position as researchers and scientists to advance community co-benefits as we increase social license and long-term durability of carbon storage. The EJ report also revealed a truth that is often all too common across environmental management projects, regardless of geography. Often that community engagement in environmental restoration projects is treated as a box to be checked. And obviously there will always be exceptions to that. Communities are informed, sometimes occasionally consulted, but often the gap that's missing is involving communities in the co-design of management objectives and management outcomes. That's not a critique of any individual project or the system at large, because we see this across systems, both in the United States and globally. But this environmental justice report does find this as more of a systematic pattern, and that has costs that can compound over time. There's another really key insight from the Delta Resident Survey that I think can really frame how we think about community co-benefits. So the survey asked people about their relationship with place. And what emerged from that data is a fundamental divide, and not geographic, but relational. And within this complex and dynamic landscape across the Delta, the survey highlights two different typologies for how people relate to place. On the one hand, there's place attachment. It's an emotional bond, it's pride, it's connection, a sense that this place is meaningful to who you are. 45% actually of Delta residents said that they're proud to live here. 41% feel attached to the natural environment. 33% feel a sense of personal responsibility for the Delta. In the social science literature, often people make claims to attachment to place as a way to describe different kinds of identities, like indigenous communities that kind of live and work in a system like the Delta. However, increasingly, we also see attachment to place show up in identities like NIMBYism, who utilize attachment to place to advance different kinds of political goals or outcomes. And on the other hand, another typology is place dependence. Place dependence is more functional reliance. This is the Delta as livelihood, not just as a landscape. 25% of survey respondents commute through the Delta, 17% work here, and 9% depend on it directly for their livelihood, and 6% of those fish for subsistence. So most importantly, these place typologies map onto different demographic profiles. Place attachment is higher among white, older, home-owning, higher income, English-speaking households, whereas place dependence is higher among Latino and Hispanic, younger, low-income, and multilingual households. Both groups live in and deeply care about the Delta, but what they need from it and what would constitute a meaningful community co-benefit will be fundamentally different. And the charts on this slide really help to visualize just kind of what I was unpacking: place attachment on here on the left and place dependent on the right. What's important here isn't any single data point. I think the distribution is quite interesting. These are not small populations. Roughly a quarter of Delta residents depend functionally on this landscape in ways that affect their daily economic lives. And so the implication for co-benefits design that resonate with community stakeholders is at the bottom of the slide here. Co-benefits designed around attachment narratives will resonate with one group and miss the communities most materially dependent on the landscape. So environmental and restoration projects historically have been better at serving at attachment relationships, scenic value, ecological stewardship, the intrinsic worth of restored wetlands. I think, as Steve was pointing out, there's some really great opportunities for ecocultural restoration that combine elements of place attachment and place dependence. And these are really real legacies that matter. But as we drive carbon projects over a long-term horizon, intergenerational horizon, we need communities with functional material stakes in the landscape to have a genuine stake in the projects, not just the people who want to kayak here or enjoy it recreationally. So you might be asking yourself, what does it actually look like to care for and design community co-benefits? And at Carbon Direct, we've kind of developed 3 principles to define whether community co-benefits are genuinely durable. Principle 1 is co-design. So not just consultation after a management plan is already made, but that the community provides input and helps shape the project from the beginning. Its structures, its priorities, its geographic scope, its potential outcomes. This is really principle 1 because it influences kind of all the other principles and has a cascading effect. Benefits you design for a community are different than the benefits that community designs with you. Principle 2 is direct and grounded. So benefits tied to real material needs, livelihoods, economic stability, food security, health outcomes. Benefits grounded in what place-dependent communities actually need from this landscape. For example, communities who fall into place attachment typology will often see a restored wetland as a benefit in and of itself. But dependence communities may need something more concrete: a job, water quality improvements that protect farming operation, a subsistence fishery that's actually functioning. So that's an idea of direct and grounded benefits. And last is revenue as investment. So thinking about carbon revenue as reinvestment in community priorities. This we see more often in the voluntary carbon market, where is often revenue from carbon projects. So that might not always apply in the Delta system. But the way to think about it is how we can use the broader scope of funding under the goals of carbon storage to reinvest in the social landscape as well as the ecological one and ecological outcomes. Some kind of mechanism through which communities can direct resources towards their own priorities, including priorities that might not perfectly align with projects' restoration outcomes or objectives. Community well-being in this right then emerges as a goal in its own right alongside ecological and ecosystem health. Digging more into principle one, we often think about that as a kind of the spectrum of community engagement. And this is often talked about in terms of a project's social license to operate. And so some of the best ways to increase social license are through meaningful and ongoing community engagement. And so this community engagement spectrum you see here is one that Carbon Direct has adapted from the Movement Strategy Center, which I recommend you all look up. And my experience, a lot of voluntary carbon projects really sit in the inform and consult stage of the community engagement spectrum. But what we're trying to push for as a field, I think, is to move towards the other end of the spectrum, involving communities, collaborating with them, and ultimately empowering them to be able to make decisions that align with restoration objectives and also could advance community priorities. All right. So I'd like to now talk about two different case studies in our work at Carbon Direct that help us think through how we might design community co-benefits. These two examples will be one in Louisiana, which is a biomethanol and carbon capture and storage project, and then a reforestation project in northern Amazon. So the first is a project designed by a developer called C2X, working in Beaver Lake, Louisiana, along the Gulf Coast. And so just a brief context here, this is a region where Black communities have borne decades of petrochemical burden. It's part of a corridor that environmental justice advocates call Cancer Alley, a stretch of the Mississippi River from Baton Rouge to New Orleans, where industrial concentration has produced disproportionate health burdens on low-income communities of color. And there's also active, organized political resistance against carbon capture and storage as a form of carbon removal in this region. Not because people don't care about climate and climate mitigation, but because carbon capture can often look like, from where these communities are standing, like the mechanisms that extend the life of fossil fuel production and fossil fuel infrastructure, pipelines, storage, that have often been poisoning these communities for generations. And so there's a long history of environmental promises made to Gulf Coast communities that never really materialized. And in reading the EJ report and the Delta Residents Survey, the Delta carries some similar but very different histories. There are communities with deep functional dependence on water operations and also diminished voice in how those operations are engaged and managed. But when Carbon Direct engaged with C2X, the project developer, the project, through our assessment, was really more operating in the consult level of community engagement that I showed you earlier. So the community members were informed about decisions, but the decisions were already kind of being made about project development and design. There was input mechanisms, but no decision-making body. And we also identified a real risk to project delivery and therefore the durability of carbon storage due to community opposition and local organizing. So to address this, we required that C2X, as a developer, undertake a structural shift in their project. The mechanism was very specific. They developed a community advisory council that had real authority on how carbon revenue gets distributed in the project. Not just a stakeholder input mechanism, not an advisory body whose recommendation the developer can accept or reject, but a decision-making body that really advises on how revenues will be redirected to the community. And this is important because in a landscape where communities are politically organized against projects like this, we believed that one of the best ways to build community trust was by giving people a meaningful voice over outcomes and how to share in the benefits of carbon projects and climate projects in a more direct and grounded way. The second example kind of takes us to a very different geography in Brazil and a very different carbon removal pathway. And this is Project Silva's Verde Vivo project in Guarujá in the Brazilian Amazon. This is a reforestation project in a deforested land for timber and then degraded through cattle pasture and grazing. And there are complex land use and political dynamics in this region with histories of corruption by state actors, dispossession of indigenous land, and shifting regional livelihoods really tied to globalization in larger economies. But this reforestation project has a planting timeline and carbon crediting period of 40 years. But the early design and restoration activities of this project are occurring now. And most of the proximate communities in this region are communities who will provide direct labor for the reforestation project and who also live, work, and depend on the region. So this is not a place attachment community. This is a place dependent story at its most fundamental. Livelihood, food security, cultural identity, all of it is woven into the same landscape that a carbon project is trying to restore. And that's a really important project design constraint and variable. So durable social license across 4 decades in this project, from a project architecture standpoint, should really see community well-being as a co-equal goal of project design. And similarly, we were working with Project Silva to develop a similar kind of approach. And they built 3 specific design features into this restoration framework that directly kind of instructive for any long-term, long horizon project. First is they broke the project into functional territories. So the project boundaries were drawn around how communities actually use the landscape. Fishing routes, farming corridors, foraging areas, and not just the biophysical footprints or the boundary conditions, but kind of like what Lisa Marie was thinking, estuarian thinking, a different scale of drawing boundaries. And that's kind of a profound gesture in this project. It says that we see how you live here, and not just what the carbon map would see. And this helps to serve place-dependent communities. Second is a binding community authority, similar to the C2X project. The project will institute a community advisory council that oversees the administration of a community development fund. The fund receives yearly distributions, both from farmer leases that they will use to plant the trees, as well as funds, once crediting starts happening, directly from carbon credit revenue. And so this community advisory committee votes on the community development fund and administers how it's distributed every year. And third is this multi-year livelihood investment across the 40-year timeline of the project. So what's unique about this model is that it's not just a few years at the early part of crediting, but it's a sustained, ongoing, intergenerational investment in community development that builds trust through a pattern of showing up year after year, and not just through a single transaction. So the explicit design goals here really help show how durable social license can be built over a 40-year project horizon. So as I close, let me pull all of this together. The chain on this slide is kind of the argument that I've been making compressed down. Governance uncertainty is the largest 40-year risk to carbon permanence in the Delta, from what we can see. Governance is shaped by trust. Delta residents have low institutional trust in the governing bodies that manage the system. Trust is earned through the quality of engagement, specifically through moving toward involvement and collaboration with community stakeholders and organizations, and not just through stakeholder engagement. Meaningful engagement, in my perspective, requires co-benefits that are actually designed for the people being engaged, and designing those co-benefits that really holds that co-design principle at its heart is one of those core functional dependent related community examples that we can see we can really drive co-benefit design with communities as partners. So the place attachment and place dependence divide is really mapped onto this problem and a guide to solving it. I think that the C2X and Silva project show us ways that we can think about it in how we might think about grounding that here in the Delta. Wetland restoration can really generate meaningful co-benefits for place-dependent communities, water quality improvements, subsistence access, flood protection. But really, I think some of the best ways is communities are involved in the design of the projects. So I'll close with a question. Blue carbon permanence lies in the dynamic interplay between ecology and politics. So how do we build capacity to meaningfully invest in both? I've tried to give some insights today, and I think from very different carbon projects. And I'm looking forward to discussing these challenges and opportunities with you over the rest of the day about how the Delta system could think about some of these community benefit co-design frameworks. The permanence this ecosystem can generate over the next 40 years will depend on whether the communities who are most dependent on it, who work on it, who fish it, who farm alongside it, build their livelihoods from it, have a genuine stake in its future. Thank you.
Thanks, Grant. So if the speakers can come up, we'll have, I think we have about 15 minutes for a Q&A prior to lunch. All right, so feel free to ask questions. I think maybe I'll start with one mainly for the first two speakers, but anyone's welcome to chime in. So there was some mention of nitrous oxide, but very brief mention. And nitrous oxide, I think, is about a 300 times more potent greenhouse gas than CO2. So do you want to comment a little bit on the nitrous oxide emissions in the Delta and what scale of problem that might be?
Yeah, sure. So I studied nitrous oxide during my PhD. So DWR actually funded a contract for UC Berkeley to measure greenhouse gas emissions, both from kind of business as usual agricultural uses and then Dennis Baldacchi's long-term eddy covariance measurements in wetlands. And so then we used some automated state-of-the-art nitrous oxide flux chambers, so measured them continuously throughout the year for 4 years. It's one of the longest nitrous oxide flux data sets anywhere on Earth. But what we really saw was during the onset of winter flooding in these cornfields, there's just an exponential growth in nitrous oxide emissions. So there's a short period, a 1 to 2 week window, where you just see 3 to 4 orders of magnitude increase in nitrous oxide emissions. And those emissions are about upwards of 40 kilograms of nitrogen N2O per hectare per year, and where background conventional corn agriculture is around 4 kilograms of nitrogen in comparison. And so really that just in a per acre space, this is some of the highest emitting areas on Earth. But when you take it back to converting it to CO2e, so using 265 as the IPCC value for converting it to CO2e, it's anywhere from 5% to 30% of your total greenhouse gas budget from these conventional corn systems. And a lot of that difference is actually how you're accounting for the carbon from the corn grown there, whether or not you're counting that in your budget. So if you just count emissions from the field, it could be 30% of the emissions. But if you then account for the emissions from the corn being consumed by cows and turned back into methane, then it's as low as 5%. So however you handle that.
Thanks. And just a quick follow-up: do you see reduced nitrous oxide emissions in the managed wetlands?
Yes, yeah. So essentially, there are no emissions that we've measured from these managed wetlands, and they might actually be small nitrous oxide sinks, but very small. But and from the carbon credit methodology, we essentially just assume 0 from wetlands. We don't assume sinks or sources.
I think there might be some microphones. There we go.
I'm Steve Lindley, Delta Independent Science Board. I have a question for Tyler. The accumulation of the thatch on these islands, is this due to a missing ecological process, or is it sort of an expected transient as plant communities reestablish?
Yeah, I think some of the idea here is that these don't have the tidal connection or tidal physical aspects of moving this material around that you would see in a tidal wetland. So we expect this to be less severe in some of our tidal restoration projects. And yeah, really this is just an impounded marsh, so it's 30 feet below sea level, and then the wind kind of just blows it over during windy years, but sometimes it just stays there. And then it's too tall to get into the water, so it doesn't decompose and so it kind of just sits there and accumulates. So that's our main hypothesis. Yeah. No tidal action.
had a question for Grant. So I liked your sort of conversations you were having about kind of giving communities a little more, not just ownership, but like actual rights and how decisions are made and how revenue is used. Could you talk a little bit more about that, of like how you design those governing bodies, I think you called them, or just a little bit more detail? Because I'm more used to kind of like what you were talking about, like stakeholder groups or advisory boards. And I'd love to just hear more details on how you guys came to that decision and how exactly you structured them.
Yeah, it's a great question. And I imagine Steve has some interesting insights too in thinking about like ecocultural restoration and involving tribes as meaningful partners and thinking about combined restoration outcomes that are also advancing cultural priorities. And ultimately, I think equitable carbon projects, when you think about it from a social and human dimension, will need to start from a place of thinking broadly about who is involved in the project. So often people call that stakeholder mapping. But the word stakeholder is often about people that become legible as having a formal stake in the project. And so that can really limit the kinds of people and communities that we might think are impacted by the outcomes of a project or who might want to have a voice in the project. So using that stakeholder mapping is a great starting exercise, and then thinking kind of more broadly about different kinds of concerns that might show up in the system. If, for example, in the EJ framework and the Delta Resident Survey, some things that came out a few times were actually migratory and unhoused communities are communities that are impacted by living in the Delta, but might not have a voice. So that's like probably a fringe example, but a way that you can think about maybe non-traditional stakeholders in a system. In some of the carbon projects that we work in, often what you'll see is the developer identifies stakeholders like the Chamber of Commerce or a lot of faith-based groups in the South, local parishes and pastors. And those are kind of what we might call traditional community development organizations. But often they'll miss community-based organizations, faith-serving organizations, environmental justice groups. So we ask that they then start to develop a framework for including those organizations as stakeholders, as they might see it in a project. And then really it's about in these private markets, in these private sector projects, it is trying to right-size the environmental justice principles with willingness to do the work. And so it's a little bit about working on kind of a case-by-case basis with the developer and recognizing who might be off-taking those credits and if they actually have a purchase or a sale lined up, so they might have more willingness to sell or there's financing already on board, then you might have a little more influence in shaping what that looks like. But what I try to frame it as is it's both a reputational risk reduction framework for them, like, hey, if you improperly engage communities and don't give them a voice, there's already history of organizing here, so you should reduce that risk by doing this. That's one way to speak the language of business. I think the other is to say there's a long-term investment that you're making in this community. And so we set this up through community advisory councils. There are other development mechanisms you'll often see in renewable energy projects called community benefit agreements through power purchase agreements, or it's actually a contract between the developer like Microsoft and a local government body that creates a contractual obligation for how revenue is shared. This is a little more informal, where it is a design element of the project that is making the project differentiated in the market that attracts buyers to buy those carbon credits. That says this is a higher quality carbon project because you are empowering communities to participate in designing how revenue will be reinvested in their communities. So that's kind of from the private sector lens, how we think about integrating these equitable carbon project development principles. But I'm kind of curious, Steve, based off of your experience working on ecocultural restoration, how you've engaged stakeholders and tribes in designing project outcomes.
Yeah, thank you. That second project that I spoke about was actually a co-design project, as you spoke about. And really, it evolved with working with Brett Milligan here on campus. He's part of the landscape architecture, human ecology group, but he really brought in a lot of expertise and with the Compass Group to do structured decision-making. So it was really more of a co-learning process, a dialogue process, where not only did we listen to stakeholders and how they could participate and what they could offer in terms of how land use should change, but also bringing in the science as well and integrating that. And it was a long-term process, and I think it's useful to think along those terms, especially in the Society Delta, where we've got private landowners, and somehow you need to integrate that process in a way that allows them, at least over the short term, to continue having enough income to support the infrastructure on the island. Now, specifically related to the ecocultural perspective, I think that needs further investigation and investment. But I saw in the Metropolitan Island project where Don Hankins and Austin Stevenot are both Miwok leaders that came in and really kind of looked at what the historical landscape was. And Don Hankins in particular, who's also a professor at California State University at Chico, had a perspective because he'd actually grown up in the Delta. And so he had this perspective of some of the land uses that were of tribal significance and ceremonial significance, in particular the historic slough that runs through the middle of Bolden Island, as well as some of the grasslands that are in the upper part of the system that really weren't mapped by Whipple and all back in 2012 when she did the analysis of the historic Delta. So it's really important to have that perspective and what those could be, what those indigenous uses could be. But even visiting in the island and looking at tules that were growing in our floating peat wetlands and seeing how they could weave and make tule boats and weave those tules into really beautiful baskets and such was also a really inspiring situation. So I think there really is that importance of involving the indigenous community and figuring out how we can incorporate that to any changes that occur.
Yeah, and I think just I'll close what Steve really highlights there is what I was trying to talk about as well, is that relational aspect that I think as ecologists, ecosystem scientists, biophysical scientists, you think in long time scales, and social relationships also persist through time, through generations. And so being able to slow down and build that relational capacity as a piece of project infrastructure, I think is a way to rethink how we do our science as well.
Thanks. Thank you all so much for this morning's talks. They're really amazing. This is a question for Grant. The distinction you drew between place attachment and place dependence was really interesting to me. And I can imagine that folks that kind of have an attachment-based relationship to place versus a dependence-based relationship might sometimes be, or might view the community in tension or in conflict with each other. You know, they have different priorities, perhaps different worldviews. And I'm wondering, when you're kind of setting up a project, if you could talk a bit about how you might reconcile tensions like that.
Yeah, thank you for the question. The place attachment versus dependence actually came out of the Delta resident survey. So that was a very nice finding from that broader survey. And those authors there did a great job of thinking about a typology that could get into some of that qualitative data. I think that in trying to, reconcile tensions is often an exercise of prioritization. And prioritization is often like a political question. And so it is trying to think about, and this is what the Delta Stewardship Council's Environmental Justice and Tribal Environmental Justice Report brings to bear in a very strong way, is that there are certain communities who have not been prioritized in management objectives and restoration objectives and outcomes. But there are other communities who just maybe by default, by their place attachment versus place dependence, those outcomes and those goals and objectives bias towards those ideals or those priorities. So it's not that place-dependent communities might reconfigure the best management practices or scientific guidelines. It's maybe that we have to think about different ways to look at, see, and measure the landscape that can include other kinds of priorities, like job creation as a value, or fair lease prices for land, but for what kind of landowners? Are there demographic profile analyses of private landowners across the Delta? What kinds of landowners are we prioritizing for restoration action? Are there landowners that are small scale owners versus big landowners? Are there corporate landowners versus small business landowners? There's ways to prioritize how we look at the landscape and see the landscape that's still on the same ecological landscape, but it's divided by political units, economic units. And so that's how I would think about trying to reconcile some of those tensions. And engage in a framework of prioritization.
Thanks. I think there's a question online, and Moose is going to read that.
Yeah, we have a question from Adina Payton. Question for Tyler. We need funds for restoration and for monitoring, yet with the complex issues of additionality and the lack of carbon credit buyers, is this even economically viable? Shouldn't this be a priority for the state to fund these activities to ensure getting to net zero by 2050?
So yeah, there's a lot in that question. Thank you, Adina. One is, yes, the state should fund these priorities, but there is not enough state funding to fund the priorities to meet these goals. And so we have to use different tools, I think, is one of the answers. And I think there are equitable ways and to handle equitable and verifiable and credible carbon accounting methods that we could use in this space to really address those concerns. There's lots of concern about additionality, yes. So, but an action today is worth more than an action in 10 years, too. So there's temporal additionality. There's all sorts of unique things intertwined with all of this. I know Barbara might get into this a little bit later, and she is really kind of the expert at thinking on all these things. But I think, it's every ton of carbon not in the atmosphere is a step in the right direction. And so how we do that and what we do that is going to have to be complicated in this complicated place. But I think if we can cover the capital costs, lower costs of entry for these projects, I think they are economically viable on a per revenue, per acre, per year basis, particularly compared to other land uses currently in the Delta.
Another couple of questions have come in online. I know reversal is less likely in the Delta than in a forest, for instance, but who pays if it does go wrong? Is the insurance embedded in the carbon pricing, or does the seller restoration entity take it on?
So I can take that one on too. There is already that built into the carbon protocol. So a certain number of your credits have to be put into a buffer pool on an annual basis to kind of cover that uncertainty in carbon reversal, and the dependence on how uncertain your specific project is in terms of quantifying that carbon removal actually depends on how much you put into that buffer pool. So if you have a higher uncertainty project, you put more into that buffer pool. Yeah, and there is a penalty for intentional reversal, so you can have credits taken away at the same point.
Thanks. Well, maybe we'll take one or two more. We are going into our lunchtime a little bit, but.
This is a question for Tyler. I want to briefly go back to nitrous oxide. You said that emission rates are exceptionally high in the Delta. Is that because of high nitrogen input application, or is it the geochemical, biogeochemical conditions below ground that results in that?
Yeah, so we actually didn't see a lot of correlation with fertilization events and these high emissions. And so there is a lot of nitrogen also being put on these systems, particularly the conventional corn systems. But really the highest concentrations of nitrate actually occur at the end of the growing season. So it is kind of a biogeochemical process of just this peat material is being decomposed and the organic nitrogen is just being oxidized to nitrate. And that pool just accumulates over time. And then once you switch that redox state to remove your oxygen, so flooding is kind of the perfect thing. So you have this high nitrate concentration, and then you flood it so you have no oxygen, and so then it's perfect conditions for denitrification, and then you just produce exceptional amounts of nitrous oxide. Yeah, it's up to 300 micrograms nitrogen per gram of soil, so also like 10 times higher than traditional soils, 10 to 100 times higher.
Was there one last question? I might have seen one other hand. Yeah.
I just wanted, I don't know if this is the right place to ask, but this notion of quality carbon credits, like who decides, how does that get measured, and how does that then get reflected in the price?
Thanks. I'll take it, and I'm curious what Tyler has to say as well. So Carbon Direct, the company I work for, works in the part of the voluntary carbon market of carbon removal credits. So not just avoidance or reduction emissions, but kind of net additional removed carbon projects. And our kind of value proposition in the market is that we really contract with the biggest buyers in the carbon removal space to help them analyze what is a high quality carbon project. And we co-develop a framework with Microsoft, who is the largest buyer of carbon removal credits in the market. We publish an update annually called the Criteria for High Quality Carbon Dioxide Removal, which is organized around 6 principles. The first principle actually is social harms, benefits, and environmental justice. There's environmental harms and benefits, additionality, durability, MMRV, monitoring, measurement, reporting, verification. And that is how we analyze the different projects across geographic space and socio-political space. So because it's all voluntary, at least in a non-compliance market, it's up to the person who's purchasing the credit to distinguish what they think is high quality. So some projects that we might say are not high quality to one buyer, another buyer might still buy those credits at a pretty significant volume of offtake. So it's the discretion, because it's a not regulated market and because it's all about difference in scientific perspectives, difference in pricing, difference in priorities, a difference in the visibility, legibility, and kind of reputational angle. Do they want to buy an engineered carbon project versus a nature-based carbon project? There's a lot of diversity in what people ultimately think of as a high-quality project. That's a little bit about how it works in the VCM around carbon removal, but I'd be curious, Tyler, how you see it working in your space.
Yeah, just I really think that that we kind of are shooting ourselves in the foot a little bit with some of the way we're defining some of all of our credits as emission reduction tons credits, because there is this reduction from a baseline emissions, and then there's net CO2 removal and storage as peat soils, and that net CO2 removal might have a higher value to certain buyers than just an emissions reduction ton credit. And so there might be a way of thinking about how we better stack these kinds of credits to really take advantage of this net removal as being a higher quality to some buyers that might get an even higher premium than just emission reduction tons.
All right, thank you. Thanks for those great talks and lots to think about. I guess we're reconvening at 12:50 after lunch.
Yeah, so lunch is provided. Moose, who from CMSI, is going to get it ready on the tables back here. So bear with us a couple more minutes, but we'll have that out and ready for you all, and enjoy mingling. A couple announcements real quick. First is I want to remind everyone that there's a field trip tomorrow morning to Staten Island Nature Preserve. That's the Nature Conservancy. Steve Deverell talked about it in his talk. If you haven't confirmed in an email this week, come see Moose or I to just let us know that you're interested. We're also, we can encourage carpooling, and so come see me if you need a ride or want to offer a ride to others, and we'll coordinate in real time. And then second, I take full accountability for dropping the ball here, but I was organizing a dinner with some speakers and moderators kind of after the event. I ended up reserving a table at Maya's in downtown Davis. And so if others are interested, so that's an announcement for everyone who already expressed interest. Yes, it's happening. After this, I reserved space at Maya's at 4:30. And if others here are interested, let me know and I can call and try to adjust the reservation. The more the merrier. So thank you. Thanks so much for the panel. That was excellent. Okay, the second session, we have 3 speakers. 2 of them are online with us today. And they are going to be kind of exploring this theme of carbon across space and time in the Bay Delta. And the first speaker in this session is Judy Drexler. Judy Drexler is a wetland ecologist at the USGS California Water Science Center. Her research is focused on wetland formation and sustainability under sea level rise, climate change, hydrologic alteration, and invasive aquatic vegetation. She has studied carbon accumulation in peat dating in a range of wetland types in California and across the country. And her work on peat soils in the Delta is really foundational to all the science that we're talking about today. So we'll welcome Judy to give her talk now. Thank you.
Thank you very much. I'd like to thank the planning team for the invitation and making it possible for me to be here today. I want to start off by talking about these beautiful old photographs of the Delta. I love to look at these because when we think of the Delta, sometimes we just think of tules, but really the Delta was a very diverse wetland region with these beautiful riparian forests, with shrub, scrub wetlands, and then a lot of seasonal wetlands. It was just an amazing place full of different kinds of wetlands and different kinds of habitats. So I hope that's something you can keep in mind. And also, okay, I'm having trouble advancing here. Let's see what I need to do here. Oh, here we go. Excellent. Okay, I also want you to keep in mind that we're going to be talking about soils. Pretty much the soils hold almost all the soil carbon, especially in salt marshes and tidal freshwater marshes like the Delta. If you're in some beautiful mangrove systems like the ones I studied for my postdoc in Micronesia, you can have some big forests, but still, even in those systems, most of the carbon is stored in the sediments. So that's something important to keep in mind. So let's try to picture the historical Delta, about 2,300 kilometers squared of channels, riparian corridors and wetlands with no hard edges. So you have different energy environments, you have different foundational species, you have different habitats, just an amazing complexity of flow rates going through this system, really, really different than it is today. And when I think of the history of the Delta, and of the history of Delta blue carbon, I think of peat. I mean, that's what I've studied for so long. And the peat, I've studied peat in a lot of places, but to imagine peat 15 meters thick at the maximum is just, to me, astounding. We dated that peat to about 6,700 years old, the deepest peats that we found in Browns Island. And back a while ago, we collected a lot of peat cores in 2005 and 2007. And then I kind of have these end members, I call them. So Browns Island is at the confluence of the Sacramento and San Joaquin rivers. It's a very high energy environment. It has high bulk density of the peats, 0.31 grams per centimeter cubed, and mean organic matter percentage of about 40. And then you don't go too far east from there, a little south of Webb Tract, and you get to Frank's Wetland, where the bulk density is about 0.14, so about half, and the mean organic matter content is about 72%, so a lot higher. And I'm showing the same figure that I made for Lisa's paper to show the carbon density. Carbon density, so if you multiply percent organic matter by about 55% in the Delta, you get organic carbon content. And if you multiply that by bulk density, you get the carbon density. So we do have relatively high carbon densities, but as you can see, we have a diversity. It's really a range. And then we also have the impact of the gold rush sediments. So 300 million metric tons of sediment going down the Sacramento can add some bulk density to your peats, and also a lot of mercury and lead, which you might not want to think about. But anyway, you could see, that did have an impact. It also formed a lot of wetlands in the whole estuary, all that sediment coming down. So let's look at the history of the carbon stored. Lydia Vaughn did a great paper in 2024 that I helped with, and we estimated using historical and modern DEMs the carbon storage. So historically, there was about 280 million metric tons or megatons of carbon stored, and then modern, we have about 143.6. So that difference is about 136.3. And we know that carbon was lost when the delta was drained. Okay, so you have this primary subsidence. It's kind of like this whole series of events that happened. So peat is predominantly water. So when you drain it, it kind of falls in on itself. So you have that drainage situation in the peat proper. And then there was some not so good management decisions such as burning. And then of course there was a lot of wind erosion. And then you have that microbial oxidation where the anaerobic conditions went to aerobic. And you have this compaction front, which we still have today, where you're continuously oxidizing. You have a compaction, and then you're continuously oxidizing peat. One of the things that we discovered that I found really fascinating is when we were coring in the farmed islands, almost all the sites had uncompacted and unoxidized peat somewhere really deep down, right above the epiclastic sediment. Now, I don't know if you've ever seen that sediment underneath the peat, but it's this beautiful blue, reduced blue clay, which is just stunning. It's just really impressive. Anyway, if you want to know more about that, you can go to that paper, the 2009 paper. So also in Lydia's paper, the 2024 paper, we looked at different scenarios for how much carbon can be regained. So if you take all the available intertidal and all available subsident, which is not practical or feasible, but let's just have this thought experiment, you could maybe regain about 8.4% of the original delta sink in 40 years. If you take a scenario that's maybe more reasonable, you can regain about 0.3% of lost carbon. And there's some other scenarios you can see there, greenhouse gas 1, 2, et cetera. But we're not trying to regain the whole carbon that was stored over 6,700 years. That's really not going to be possible. But we are trying to help California achieve carbon neutrality. So all of these things, of course, count for a lot. And so what we're really talking about is using blue carbon restoration as a negative carbon emissions approach. Now, there's a lot of people in the room who know way more about these things, additionality, durability, and leakage than I do, but I can just tell you some of the basic definitions. So additionality is what people talk about and they're very concerned about. So if you have a carbon project, you don't want the emissions reductions, you want them to be additional. You don't want them to be what would have happened under a business as usual scenario, okay? I know a bit about durability, so that's really how long is that carbon that you store going to last in situ. And then this other thing that people talk about, and it's very important too, is leakage. So if you're going to increase carbon storage somewhere or decrease emissions, you don't want to increase emissions somewhere else. So that's pretty important, and there's a lot of references on this. I put some of them below, but I'm sure people in the room can also talk about this very, very well. So, but in the delta itself, we have special considerations that we have to think about. We have to find land in order to restore these wetlands that's at suitable elevations and that has migration space, so we can think about them being sustainable with sea level rise. We always have to think about balancing, so having these restoration goals and balancing them with water operations current and future. And also there's a lack of data on there's some excellent data, absolutely, but there's a lack of data on certain wetland types such as riparian forests or these scrub shrub. And there's also different management regimes we could still try that haven't been tried yet. Levee failures, we're going to have them. Steve Deverell talked about those. And how are those going to affect these tidal wetland restorations? That's something we might want to think about. And then we also really want to think about creating an overall strategy for aquatic restoration, of which blue carbon is just one part. And Lisa's paper in 2023 definitely got into that. So as a wetland ecologist, today I'm going to talk to you about some basic scientific principles for restoring blue carbon. The first is really you got to base restoration on sound principles of wetland science. And I'll be talking a lot more about that in later slides. You have to learn from prior restoration mistakes, and there were mistakes made. Let's face it, in the Delta and elsewhere. Let's not make them again. Let's learn from them. Restoration is an art and a science. We want to view each restoration as an opportunity to keep learning, and then like for instance, put in a little experiment in your restoration or a little study of something. Continuously incorporate your new insights. And if you take anything away from this talk today at all, I hope you take away that we need to understand peat formation as an ongoing process responding to the environment. So it's just continuously responding to things going on in the environment, whether it's a drought, an atmospheric river, sea level rise, what have you, it's constantly changing. That's important to keep in mind. So there's a lot of factors controlling carbon accumulation in restored wetlands. I could go through each of these in a kind of boring way, but I've decided instead I'm going to give you some examples from all the places I've studied, or some of the places, and not all, I don't have time for that, but some of the places I've studied. So let me take you first to one of my favorite spots, which is the island of Molokai, Hawaii. And here's an example one about how drought or hydrologic alteration can affect wetlands. And we evaluated 12 coastal wetlands on the south shore of Molokai. It's very undeveloped there. It's an amazing place to try to do restoration. And we wanted to understand, their potential for being restored, which ones are really good candidates. But you can see that there's a lot of impacts. These are degraded sites. They're very dry from stream diversion, but also from drought. There's actually salt precipitating out on some of them, and a lot of invasive species. So we took a look at these, and we took some very basic measurements, depth of water table, percent organic carbon in the surface soils. And I want to point out one site that really caught my eye very early on, because first of all, the water table level was really close to the surface, even though it was so dry there. This Kaupapalo'i o Ka'amola site is an agricultural wetland where they grow taro. And historically, it used to be a site like that. And then they restored it just recently, in about the last 10 years. And this site also has organic soil, and only 2 of the sites had organic soil in that figure, Ipuka, that's a floating mat. So of course that's going to have a lot of carbon in the floating mat, but the soils are described in the rest of the ones. And there's 2 that had organic soils. And so again, I was very curious about this site. And as you know, you need hydrology to be consistent to support coastal wetlands. So we looked at that site. It had the highest water table, and it actually turned out to be a coastal fen with lots and lots of deep peat. In fact, when I dug a pit about 3 meters from the ocean, the water in that pit was fresh. So imagine how much groundwater is coming out. So, it was the first coastal fen we identified in Hawaii. Well, why am I telling you this now? Well, there aren't, I doubt, any coastal fens in the Delta. There used to be a bog in San Francisco, but that's another story. But there are Delta wetland types we don't know much about. Riparian wetlands, scrub shrub, and even these beautiful fern grottos that Steve Deverell and I and Christian Defontaine were in many, many moons ago. So I'm going to talk about a few lessons that have been learned. So without the right water table level, soil conditions will not be conducive to native wetland plant growth, which is critical for long-term carbon storage. Okay, so now I'm going to take you all the way to the Nisqually National Wildlife Refuge in Olympia, Washington, where a dike was removed after 100 years with no tidal exchange. And that site had gone through a lot of land surface subsidence. And so there wasn't proper grading before restoration. And as you can see below, the site, Sixgill Slough, at least back then when we did this study, did not have a lot of vegetation. I think it's improved somewhat since then. So it really didn't have a lot of vegetation. And then there you see Jim Orlando standing in front of Animal Slough, the historical reference site, with this beautiful Carex lynchbii. This is a brackish marsh in Puget Sound. So what we wanted to do was compare these sites about 7 years after restoration. And we looked, first of all, at the vertical accretion rates. The restoring site had about double the accretion rate of the reference site. Now it is in a bowl. It was in a subsided bowl. So it's a very good receiving ground with a lot of accommodation space, right? So then we also looked at carbon accumulation rates, and we compared the restoring and the reference. And even though there was no statistical difference because of a lot of variability, that restoring site seems to be collecting a lot of carbon, even though I just told you that you need plants to do that. So we were scratching our heads, and we said, where is this soil carbon coming from in the restoring marsh? So we did a Bayesian stable isotope mixing model. We took carbon samples from every possible source, and we found something really interesting, that the carbon was coming from allochthonous sources, mainly the nearest ones. What was the nearest one? That beautiful Carex lynchbii marsh. So we learned a few things in practice here that it wasn't really that new, like lesson number 2, initial surface elevation is critical for establishing hybrid period and initiating plant growth and soil carbon storage. That's pretty well understood. But lesson number 3, I thought was pretty interesting. Lots of carbon can be coming from outside the system in which you're working. So if you have a certain project boundary and you're getting a ton of carbon, and a lot of it is allochthonous, which means outside the system, that usually can't be counted, or only a percentage of that can be counted for carbon credits. That's a very important thing to understand. All right, so let's come back to the Delta. That's where we want to be for this symposium. And I worked with Jim Morris and folks at SFEI to come up with this coastal wetland equilibrium model that was developed for delta marshes. And it had a front end that actually used my marsh cores to reach the equilibrium, the run-up to the modeling, to look at marsh sustainability in the future. And we found some very interesting things doing this model. First of all, we found that delta marshes can tolerate centenary sea level rise as high as 200 centimeters because of the large elevation range of the tules. So the tules can grow, especially Schonoplectus californicus, can grow under an amazing range of elevations, very low to quite high. Also, the marshes are sitting in a pretty good elevation right now, most of them in the Delta, which is really good to know. We also looked at this thing called a tipping point. For a typical delta marsh, the tipping point at which vertical accretion rate can no longer keep up with the rate of sea level rise is greater than or equal to 50 years. So this gives us some time to really improve stuff and think about things to preserve the marshes that are already there, and also to get some marshes restored, hopefully soon, before sea level rise really accelerates. So another thing that we looked at was simulating atmospheric rivers, which to me was very important. And we added this to the model. We found that adding triennial additions of about 6 millimeters of sediment via episodic atmospheric rivers moderately reduced marsh drowning and increased resilience. So this was really great to know. So every time there's a huge atmospheric river, you can think, I bet the marshes are really getting some good sediment from that. All right, so now if you take a deeper dive into marsh equilibrium theory, you can learn about a sweet spot for carbon accumulation. So let's look at this 7A, relationship between primary productivity and relative marsh elevation. Now, most marsh plants live between mean sea level and mean high water. And the relationship you're seeing right there is for Spartina alterniflora, but it can be determined for other species. In fact, Chris Janicek, who's sitting out there in the audience, did such a study. And so you can see that there's a sweet spot for the maximum biomass production. So that's an important thing to understand for your foundation species in the wetland that you want to restore. And then also vertical accretion rates are dependent on both mineral sediment and biomass. And if you're low in the tidal frame, you're going to have more reliance on the mineral sediment. And if you're higher in the tidal frame, it's more going to be the biomass. And again, that relationship really depends on the plant that is the foundation species in the wetland. And then last but not least, your relative marsh elevation can be shown as in relation to the rate of sea level rise. And of course, beyond a certain point, you're going to have just this drop off and you're going to have drowning of your marsh. So lesson number 4, tidal wetland carbon storage varies with elevation and sea level rise. And if you're interested in this, there's just a bunch of different references that you can look at that I put in right there. Okay, example number 4, invasive aquatic vegetation. So long-term delta invasion of submerged invasive aquatic vegetation, especially Egeria densa and floating / terrestrial Ludwigia hexapetala. So we wanted to determine, these guys have been around a long time. They really went crazy like in the 90s, but they've been around for a very long time. We wanted to determine their effect on carbon accumulation, carbon storage in native delta marshes. So picture a generic delta channel. That big rectangle is the native Schonoplectus marsh. And unfortunately now, Egeria densa, which is submersed, is really lining almost all of these marshes. We found out in our 2020 paper we published that it's a novel sediment and carbon sink. And then another person working on the project, Paul Work, his paper on this project, we found that this Egeria densa is actually channelizing the flow in the channel. So the flow is kind of going down and is channelized by all that vegetation, those patches of Egeria densa. And then Jessica Lacey showed that sediment is actually being directly blocked by Egeria densa for going into the marsh. And we talked about how accretion is sediment as well as organic buildup of roots and so the plant productivity. And then last but not least, Another project I did with folks at UC Merced, we looked at the impact of Ludwigia hexapetala. Now, Ludwigia, when it's a floating invasive plant in open water, but now it's actually going into the marshes. And when it goes into the marshes, it's amazing. It can then go upright and actually outcompete tules. And how does it do that? Well, we showed that it does it through allelopathy. It actually goes in and poisons them and kills them. And why is that important? Well, Ludwigia has very wimpy roots versus the native Schonoplectus, which has very beefy roots. And that creates a lot of carbon storage. So if you're going to lose a lot of your tules, you're going to lose a lot of carbon. So lesson number 5, understand the ecosystem disservices of invasive species and really try to eradicate and control them as soon as possible. Okay. Last but not least, and this is something I'm really interested in lately, is future uncertainties in blue carbon restoration and blue carbon storage. So some key questions are, will wetland carbon accumulation change in the future because of climate change and the delta because of water operations, sea level rise? And will that carbon storage be durable over the long term? So of course, this is getting into the issue of permanence. And the way that I'm looking at it now is, what are the mean blue carbon residence times for different wetland types? And how can we think about that? And so in that figure, you can see in the yellow text, what is the mean residence time here? And can we really determine that for different wetland types? That's something that I'm collaborating with some folks right now. So anyway, I want to thank you so much for having me here. And that's about all I have today. Thank you so much.
And next up, we have Dr. Tomoko Komada is talking. Tomoko is a marine biogeochemist at the Estuary and Ocean Science Center at San Francisco State University. And she is interested in understanding biogeochemical processes that transform organic matter and sediments. And she specializes in the detection and modeling of natural carbon isotopes. So let's welcome Tomoko to the stage.
Thank you. I'd like to thank the planners for organizing this and for having me here today. So I'm going to start by editing the title. In order to focus the discussion, I'm going to be speaking through the lens of salt marshes, specifically mineralogenic ones, which are rich in mineral particles. But what I'm going to talk about should be broadly applicable to other blue carbon ecosystems, with the exception of really organic like peats, which there's a lot of in the delta. But there are lots of salt marshes of this kind down in the estuary. Okay, so what I'd like to do is to convince you that salt marshes are both really good repositories of organic carbon, and they are excellent reactors that convert organic carbon into other forms. And that carbon cycling in salt marshes is complex, and because of that complexity, I think that translating rates and processes to climate benefit is also complicated, and I think it should be done with care. So just some abbreviations. I'm going to be using OC for organic carbon, POC, DOC for particulate and dissolved organic carbon. DIC is dissolved inorganic carbon, and that's the sum of carbonic acid, bicarbonate, and carbonate. And because I'm a marine person, I usually work with sediment. So when I say marsh sediment, I mean marsh soil. Okay, so salt marshes as repositories of organic carbon, I think this is a picture that comes very naturally to just about all of us. So here we have carbon, organic carbon that is delivered to the system, and the system being the sediment column, as we just heard from Judy. That's where most of the carbon is, below ground. And the carbon supply is coming from primary production occurring locally, as well as carbon that is imported from outside of the system. But this is, as we know, too simplistic. It's not very realistic because the system is very much alive. So these wiggly things are my attempt at drawing benthic organisms like worms, clams, whatnot. So they're heterotrophs. eating stuff, and then the mud is essentially teeming with microbes, constantly converting organic carbon into other forms, resulting in a net return flow of carbon in the form of gases like CO2, methane, depending on where you are, and also carbon exported laterally as DIC, DOC. POC can also be resuspended and advected out. So the question I want to address is how big is the output relative to the input? In other words, how effective are these systems at being a reactor? So this is where my marine background comes in. So I'm going to talk about use burial efficiency here. So this is a metric that's been used in marine sciences for many decades. So this is defined as the organic carbon burial rate at depth being rather subjective. But generally, carbon transformation rates are high near the surface of the sediment, and maybe several tens of centimeters below, the rates go down. The rates never go to zero. You can go hundreds of meters below the seafloor, and you still see microbes chugging away, albeit a very slow, low rate. But so as the rates go down and go down to some low level, you can calculate the carbon burial. So there's the carbon burial at depth divided by the total amount of organic carbon that is. I'm having a bit of a difficult time with the pointer here. Where'd it go? I lost it. Oh, there you go. Organic carbon supply to the surface. Okay, so I'm going to show you some marine data first. So I'm going to show you burial efficiency on the y-axis, and then on the x-axis, this is sediment mass accumulation rate. So this is not vertical accretion rate, just amount of, the mass of material. So here's what we call typical or normal marine sediments underlying oxic water column. So as you can see, burial efficiency increases with sediment accumulation rate, which makes a lot of sense because as particles are raining at a faster rate, it'll be buried faster, essentially surviving the high reaction rate top part of the sediment column. So burial efficiency so clearly is dependent on sediment accumulation rate. It's also dependent on oxygen level. So shown here in the black filled squares and circles are oxygen depleted sites, so either just low in oxygen or just completely anoxic and sulfidic sites. So you can see that they have relatively high burial efficiencies. By the way, the blue envelope is just for visual purposes. And then we can also decrease burial efficiency, and we see that in major river deltas. So these are data from the Amazon, Mississippi, Fly, and the Changjiang. So these are also referred to as fluidized beds because it's very energetic, and essentially the whole seafloor is like churning. Okay, so and some people have referred to these as incinerators because they have low burial efficiency. So they're really good at burning through some of the carbon. So then the question is, where do salt marshes fall in this figure? So I I estimated this two ways. First is to look at so organic carbon burial, reported burial rates divided by, so total input equated as net primary production. So this is gross primary production by local plants minus respiration done by the plants, plus whatever allochthonous carbon that is coming in. So that's one way to do it. And the other way is saying that the carbon that is buried, lost my pointer again. Where'd it go? Oh, there it is. I have bad eyesight. Okay, so here's carbon burial plus output, the sum of these being the input. So organic carbon burial at depth divided by the sum of burial plus sum of burial and the output rate. Okay, so estimate one, I use numbers from Alongi 2020. So I was able to find global OC burial rates and net primary production in salt marshes. So using those numbers, I got burial efficiency of right around 22%. but this might be on the high side because it ignores allochthonous carbon input rate, which I was not able to find in that publication. Estimate number 2, so this is looking at lateral export. So I got the numbers from Santos et al. So the denominator here is the sum of burial and lateral export, this guy. Okay, so again, I got 22%. I'm sure this is probably a coincidence, but this might also be an overestimate because in this case, what's missing from the picture is gas exchange. So then I had to find the sediment accumulation rate. I was only able to find one number in the literature, not that I spent too much time looking for this. So I'm sure there are lots of people in this room who might know where I should go to find additional estimates. So if you know, please let me know. So I got an estimate of 0.28 grams centimeter squared per year. So if I plot this in that log space, it looks like this. So salt marshes sit right here. So pretty high sediment accumulation rate. In terms of burial efficiency, you know, it's kind of on the low end of what we call normal marine. Okay, so they seem to be pretty good reactors. So this is a log plot, and some you know that in a log plot you can plot just about whatever you want and still see a relationship. So here's a same actually more expanded data set showing different types of marine depositional environments, but now the y-axis is linear. Okay, x-axis is logarithmic. Okay, so we have the normal or typical marine, and then here's the oxygen depleted zone at the top, and here's the fluidized bed deltaic reactors here, and then we have extreme accumulation rate. So this cross is the Ganges Brahmaputra, and then this one up here is the Rhone River. And then SMRs are, this stands for small mountainous rivers. These are small watersheds that drain very, very steep terrain in high, and these are present in active margins. So they dump a lot of mud like a chute during storm events, and they have very high burial efficiency. So then we can plot that same data on this space, and then salt marshes sit pretty low. So they have very high sediment accumulation rates, but in terms of burial efficiency, they don't look like rock stars here. Another data set, so this one is from Reitmeier et al., Nature Communications, 2023. So they looked at net primary production and various ways to lose carbon from the system from 45 mangroves and 16 salt marshes worldwide. So the top one is mangrove, lower one is salt marsh. So let's see, so the total is NPP, and then the dark brown is burial. Okay, so burial over NPP is on the order of 10%. And then blue is CO2 outgassing, and the greens are all lateral export. So it's not that there are too many estimates here, but so far of all of the data are pointing to salt marshes having pretty low burial efficiencies. But why might that be? So this actually isn't too surprising, knowing that organic carbon degradation is promoted by what's called redox oscillation, which is instead of having a system continuously oxic or continuously anoxic, if a system switches between oxic and anoxic, it tends to promote overall degradation, and also co-metabolism, which is mixing of refractory and labile substrates. Having them in physical proximity of each other tends to generally overall promote degradation. So shown here again are marine systems. So on one extreme, you have steadily accumulating systems. So this would be an example of anoxic or low oxygen environments, not enough oxygen for macrofauna to come and mix the sediment. And then you have slightly more oxygenated, bioturbated environments. And then on the extreme end, we have the fluidized mud reactors at the mouths of major rivers. So if you think about where would marshes, mangroves, I go ahead of myself here. So as we go from left to right, okay, we see increasing physical mixing, more efficient exchange of oxidants, and mixing of substrate, and also flushing of metabolites. So as we go from left to right, there's a general decrease in burial efficiency, and the flip end of that is greater burn through of organic material. So I would argue that mangroves, makes sense that mangroves and salt marshes sit more towards the right on this scale. Okay, so but this doesn't mean that blue carbon ecosystems don't hold a lot of organic carbon, because they do. So because even though there's a lot being lost at the side or as gases, because so much is being deposited, a lot is still being buried on an annual basis. So as you can see, seafloor is way, way bigger than blue carbon ecosystems, but these three green bars put together, they totally rival burial in the ocean. But then this totally begs the question, so salt marshes, therefore, are both excellent repositories and I think very effective reactors, okay? But then this begs the question, what kind of organic carbon is being captured? Because we can't forget that not all organic carbon is created equal, and depending on what is preserved versus what is not, I think really affects the way we calculate the climate benefit implications. For example, so there's a lot of evidence building now in the literature about what kind of carbon is buried. Well, a lot of old stuff, so like 10 to the 2 centuries to millennia old organic carbon, it tends to be rich in terms of what's buried because the degradation rate constants are low. And we're not talking about carbon that aged within the system, because we also see that this kind of old organic carbon is coming in from outside systems, and in particular they're associated with minerals like clay minerals. So clay minerals don't grow in marshes, they came from upland systems, and wherever clay minerals go, there's always organic carbon stuck with them. So, and this also makes sense because we've known for quite a while that if you sample POC suspended in rivers, there's a lot of old organic carbon in there. So what does this mean for climate benefit? So, the 2 disappeared. It's not carbon monoxide, it's carbon dioxide. The two is behind the top arrow. You can see the little bit right there. Okay. All right, so this is going from different laptops. All right. So anyway, so the whole the climate benefit of blue carbon is that I keep losing the. Where is it? Did I lose it? Does anyone see the cursor? Oh, there it is. Okay, right. So plants take up CO2 and then create biomass, and some of that is being buried. So that's where the climate benefit lies. But if we have ancient carbon that was photosynthesized centuries or millennia ago, and then that aged in the soil profile, that gets eroded and then gets trapped here, that has zero net climate benefit because this carbon is completely cut off from present-day CO2. So I've also heard of arguments that, well, if we don't trap carbon, the old carbon here, it's going to get exported and then it's going to get oxidized. But I think the jury is out on that, at least based on the burial efficiency data that I showed you. Okay, so linking climate benefit is not, linking to climate benefit is not straightforward, at least for the repository side of salt marshes. So how about the reactor side? Is there any climate benefit there? Well, so we all know that, losing the thing again. I have really bad eyesight, that's my problem. Where is it? Up, other this? Okay, so if the carbon goes out back to the atmosphere, obviously no climate benefit. It would actually be worse if we have allochthonous old carbon that aged somewhere else, gets processed here and goes back out as gases. That would be a negative impact. Lateral export of DOC. I don't know the literature too well, but if most of the DOC is freshly produced, so I studied DOC in the ocean, my guess is that a lot of that will be oxidized to CO2, at least within like annual decadal timescales. I'm sorry, back. POC, if it's labile, it's going to get oxidized pretty rapidly. All the refractory material, as I discussed earlier, I think the jury is out on that one. I think the biggest promise lies in DIC, lateral export. So in the absence of oxygen, if organic carbon is degraded by sulfate reduction and the reduced sulfur is then locked up as pyrite through reaction with iron, and there's plenty of iron in these systems, that results in net alkalinity production, and the carbon is exported in the form of bicarbonate, and it's going to stay as bicarbonate outside of the atmosphere for a long time. Another way to get climate benefit is carbonate dissolution, so that also adds alkalinity and results in DIC lateral export. But I don't know how much carbonates, usually there's not that much carbonates in muddy systems, but you do see carbonate platforms where some eelgrasses grow, I believe. I just want to end by saying that carbon cycling in salt marshes is complicated. Just sort of started introducing lateral export. There's a lot about lateral export, and we could spend just days talking about this. I think that more study needs to go into looking at lateral carbon export, especially DIC. Okay, so take-home messages again. Salt marshes, I think, are excellent repositories as well as very effective reactors of organic carbon. And then carbon cycling in salt marshes is really quite complicated. And I think we need to look more on lateral export, especially DIC. And because of these complexities, I think that translating rates and processes to climate benefit is also complicated and should be done with lots of care. Thank you.
Okay, thank you. Just a reminder to jot down your questions, save them for the panel discussion after our third speakers in the session. Those last two talks were a great reminder that nothing's as simple as it seems, and these are really complicated systems. Okay, do we have Jim online? Okay, so our next speaker is Jim Holmquist. He is a research scientist at the Smithsonian Environmental Research Center, or SERC, and chief scientist on the Coastal Carbon Network, where he focuses on improving predictions of how wetlands respond to change in time and space by leveraging large data synthesis, geospatial information systems, and ecological forecasting techniques. And so he was also led the team that built the Coastal Carbon Atlas, which is a global atlas or database with data from over 16,000 soil profiles. So thank you, Jim, for joining us remotely. Sorry you couldn't be here in person, and we look forward to your talk.
Hi, everyone. Thank you so much for inviting me to talk. Thanks to Lisa Marie and Moose. And I'm really sorry I couldn't be there in person, but I'm really grateful for everyone for accommodating me. I'm coming to you from College Park, Maryland today, but I normally am a Southern California resident, so not too far from where you are, at least compared to where I am now. Can people see my screen? I guess I can't hear anyone.
Yes, we see it. We see it, and we see your
Okay.
face as well.
Perfect. So today my talk is called Looking Forward by Looking Back. And so I'm going to talk a lot about wetland soils as archives of change, but also engines of future prediction. And I really wanted to acknowledge my funding sources up front, the Compass Project from Department of Energy, NASA Carbon Monitoring System, National Science Foundation, and my home institute, the Smithsonian Environmental Research Center. Okay, so just a quick framing. The reason that we're here, that I'm here talking to you about forecasting and predicting coastal wetland carbon storage is because California has been making monumental investments in decarbonization over the last few years. Due to Assembly Bill number 1757, the California Natural Resources Agency has produced really assertive acreage targets for coastal wetland conservation and restoration. That's 12.2 thousand acres of conservation and restoration a year of additional conservation and restoration to up to 2045. And this includes coastal wetlands, inland mountain streams, seagrasses, and of course, delta wetlands. As part of this Assembly Bill 1757, the California Air Resources Board is responsible for archiving and tracking all of the carbon that gets stored from natural and working lands restoration. In fact, they just put out the 2025 natural and working lands carbon inventory. We're really excited to see that published. And of course, taxpayers like you approved Proposition 4, which includes $10 billion in funds for various actions related to addressing the challenges of climate change. And that includes a large amount for sea level rise and coastal area adaptation, as well as land conservation and habitat conservation. So this is a very exciting space with a lot of attention right now. So another little bit of framing, and Judy went over this a little bit, but no harm in a little bit of review. We quantify our carbon, our baseline carbon removals, and we fit our models of future carbon using paleo-environmental techniques. So soil cores, such as this one that my supervisor, Pat McGonigal, is holding, basically punching a hole in the ground with a tube, fancy way of saying that. And then we perform a couple different analyses on those soils that we extract from the ground to calculate a carbon accumulation rate. That includes the carbon content of the soil, that's one variable, the density of that soil, that's the second variable, and divide that by the number of years that it took that soil to form. So the goals of my talk are to introduce two open source data tools that we have at our disposal for making these calculations of carbon accumulation rate. I want to demonstrate a case study from a wetland on the Cirques property near Annapolis, Maryland, that shows how we can fuse both models and data to make a forecast. And finally, I want to close by discussing some ongoing development and future opportunities. So the first product that I want to tell you about is the Coastal Carbon Atlas. This is a global synthesis of tidal soils data. We have 16,165 soil profiles worth of data from around the globe. This is a free open source database. We don't even take your email address. You can go online right now and search this. It's constantly growing. And the important thing is that each data point in here is traceable with a link and information that points you back to the original author and the original study. So this product is not a single monolithic synthesis. You can think of it as the hub of a spoked wheel, where all of those spokes point back towards the original authors and all of the hardworking people who contributed to this community data synthesis, which is, I think, greater than the sum of its parts. California has a very large data footprint in our database. We've done some analysis creating data quantity, quality, and coverage metrics for US states, and California scores highly. You can see ranked number 2 in aggregate on multiple data quality, quantity, and coverage metrics. We have a total of 260 soil cores from California. Most of these are from the Bay Area. 73 of these have the right types of data that you can use to calculate carbon accumulation rates. And this is a fun thing for me to announce. 58 cores are being added soon, with 14 that have carbon accumulation rates calculated. This is actually coming out of my old lab group at UCLA, Lauren Brown's dissertation. We are publishing a data paper. It just got accepted a few days ago, so hopefully in the next few weeks I'll be able to send this around, and you'll see we've been able to add to the growing amount of information we have for our wetlands in California. So soil measurements and radioisotope dates that we use to calculate that number of years figure have uncertainties and biases that make them imperfect observations. So if we kind of go through those elements of the calculation I talked about one by one, we can see we have our organic matter content. We have studies that show different decisions people make in the lab, different lab protocols can bias organic matter content a little bit higher or a little bit lower. We have scale error. Similar to that, the bulk density of the sediment can be influenced sometimes by a coring method. For instance, methods where you really have to hammer the core in there with a like literally hammer it in there can potentially bias your densities a little higher. And then the types of techniques we use to date our samples have a lot of uncertainty too. For instance, we have our two examples here. We have radiocesium dating, this CS137. This is looking at that peak of the 1963 peak in nuclear fallout from atmospheric weapons testing. These peaks can sometimes be strong, sometimes be weak. It really depends a lot on atmospheric deposition, erosion, and sometimes you can get mobility of the cesium within the sediment that can smear the peak. So these are clues, but they're not not any clues, but clues that you have to take with a grain of salt. Similarly, we have lead-210 dating. This is looking at the fallout of naturally occurring lead-210 out of the atmosphere. And as it's buried over time, it decays exponentially and approaches this background level. This dating method could be influenced by, the accuracy of it can be influenced by how far down you go, how certain you are that you've reached that background level. And both these methods benefit from having more continuous samples and just more samples overall, which are sometimes hard to get because these are expensive dating techniques, and scientists need to make trade-offs on how many samples they run versus how many sites they run. There's a lot that goes into this. So if we're not always 100% sure about our data, where else can we turn to get good assessments? Well, we can turn to our models. And what I'm going to talk to you today about is a model that's really closely related to SWIM, the Coastal Wetland Equilibrium Model. In fact, it has the same author, Jim Morris, who I work with on a lot of these projects. We call this version the Cohort Marsh Equilibrium Model. It's an ecological and a physical model of how soil evolves under rising sea levels. It has two major components: a dynamic feedback between flooding, elevation, biomass, and sediment trapping. And then it has a second component, which is a depth-wise accounting of what happens to different annual mass pools that are made up of organic mineral matter, organic matter, and live roots. So you can see that here we every year the model will calculate where it is in where the elevation is within the tidal range. It will predict plant biomass based on the growing tolerances of the plant species you give it. It'll trap sediment in a sort of surface layer pancake of sediment. And then that above ground biomass will inject roots underground, and roots will turn over into a fast decaying organic matter pool and a slow decaying organic matter pool. And as roots turn over and as cohorts get buried year after year, cohorts swell and shrink and get integrated into the deeper parts of the soil. So this model has a couple different ways that it predicts the type of a soil profile you'll get. You can give it a few different sediment parameters, including suspended sediment concentration and a capture rate, which describes how much of a sediment budget will get retained by the plants on the surface. We have some above ground biomass parameters. We have these growing tolerances that define a skewed parabola. We have our below ground biomass, which we describe using a root and rhizome to shoot ratio, a below ground turnover rate, and a root depth descriptor. We have our decomposition parameters, which include the slow pool allocation. So how much carbon goes into that slow pool versus how much is returned to the atmosphere relatively quickly. And of course, the decay rate. And then all of this is really controlled by these soil structure parameters, which turn the accumulation rates into elevation change. Of course, models are abstractions and they're not perfect representations of reality. As George Box said, all models are wrong, but some are useful. So now that I've been a little pessimistic about data and models, where do we go from here? Well, I tend to prefer using Bayesian methods that let us make the most out of our data and our models. So if you're new to this terminology, you can think of Bayesian methods as a school of statistics that treats everything you deal with as a probability distribution. So we don't think in terms of fixed values in Bayesian statistics. We think of some things being likelier than others. So you can think of a Bayesian analysis as having a few different components. A prior distribution that represents our hypothesis for how the system works. We have our data or our likelihood, which is supposed to be our evidence. And you can see these are both probability distributions. And then we have our posterior distribution or our conclusion, which is dependent on the relative strength of our priors and our data. So in a case where they have about equal weight, they're about the same width, the posterior or our conclusion will be somewhere in the middle of our original hypothesis and our new evidence. Dealing with data and models in this way has a few advantages. First, we are forced to actually quantify our model uncertainty as well as separate that from our observation uncertainty. So the very fact that we have to go through this exercise means we have to be explicit about where uncertainty is in both our data and our models. It allows for data model fusion, which can be more powerful than either method on its own. It allows us to fully propagate uncertainty into our predictions, and it allows for structured recommendations of new research priorities. So here's where we get into a bit of a case study. So me and my co-authors ran the cohort marsh equilibrium model in a hindcast. So going from 1928 to 2018, where a core in a low marsh was taken by Tyler Messerschmidt and Matt Kerwin. And you can see here that in blue, those blue lines are just a random grab sampling of a lot of model iterations. To do these types of statistics, you have to run thousands and thousands of different iterations on different settings. So the blue is a random grab of those samples. The white and the black bars around them, those represent our data and our data uncertainty. And the gray represents the latent states or the statistical compromise between our model uncertainty and our data uncertainty. And you can see we have this for our age depth model, our number of years that go into that carbon accumulation rate calculation, our bulk density, our organic matter content, as well as our elevation. Because we have uncertainty defined in both of our model and the parameters in our model, we can combine that uncertainty with the uncertainty in the sea level rise scenario we have to drive this model into the future. So what we have here on the left is kind of the funnel of uncertainty going to the future for sea level rise from Robert Kopp's 2014 study. And these scenarios are available globally. This is just the one for the Annapolis Tide Gauge Station. What we see here is into the future, the increasing likelihood that the marsh converts to open water increasing. And in fact, by 2060, we cross a 50% threshold that we're likely to lose this marsh. We never reach a 100% probability of marsh loss. In fact, there are some scenarios where the marsh persists into the future, but because we're working in probabilities, we say it's more likely than not at this point, given our evidence, that we think this marsh will convert to open water by 2100, unfortunately. We can also look at what this does to carbon accumulation rate. We see that our change in carbon accumulation rate relative to a 2018 baseline declines into the future as that likelihood of loss to open water increases. Once again, this is for a marsh on the other side of the country from you. It has a lot of risk factors that we don't have in San Francisco Bay, but the method and the philosophy here is what I want to instill in you today is a useful thing no matter where you are. Because we run so many model permutations, we can also look at what the model is sensitive to. At this site, the model outputs were most sensitive to the slow pool allocation term, parameters that have to do with plant productivity and organic soil density. And when we rank these, we can say, hey, this is really our shopping list for new studies. These are the things that if we improve, we can have a more accurate predictions going forward. Finally, I wanted to let you all know about some things that are coming around the corner. The California Air Resources Board is currently funding new work to allow for this type of data model fusion on a larger scale for California. So me, a postdoc in my lab, Abby Lewis, and a few others are working to integrate the cohort MEM model into PCAN, which is the Predictive Ecosystem Analyzer. It's a software package that allows for these types of Bayesian or probabilistic forecasts to be made in a standardized way. And I really hope that this is leading us to a place where we can have these two loops that feed back on each other, an iterative forecast cycle where we make probabilistic forecasts. We collect new data to validate our forecasts, and we find what we're doing wrong, and we improve iteratively. At the same time, managers are using forecasts to make decisions, collecting monitoring data to evaluate their decisions, and generating scenarios to drive our models. Experts like you are going to be really important in assisting us in making sure that these data and modeling tools capture the dynamics of the delta. For instance, the really unique history of water table drawdown and subsidence are things that I think the model could do. And I'm working really hard to make the R package of our version a lot more flexible to include things that we haven't really tackled in the scientific literature yet. But learning more about the delta and the specific needs and the types of management questions that you want forecasting tools to answer is going to be really interesting and helpful for me. So to conclude, California's coastal restoration investments need paleo and soils data to characterize baseline carbon accumulation rates and to fit models of future wetland response to sea level rise. However, models and data are imperfect tools. Bayesian methods can allow us flexibility to leverage both, propagate uncertainties in forecasts, and develop structured research priorities. And finally, CARB is investing in data model infrastructure, but we need experts like you to help us inform scenarios. Thank you very much.
You, Jim. And now I think we have like 15 minutes for a panel discussion. Is it possible to get Judy and Jim on the screen? We'll have two virtual panelists. And Tomoko, do you want to come? Do you want to stand here or there? Where are you more comfortable? Yes, sure. And maybe now's a good time for me to introduce myself. Sorry that I didn't. Everyone's wondering who's this lady talking to us. I'm Brooke Eastman. I work at the Delta Stewardship Council, and I helped organize this event. My background's in forest carbon, cycling, and carbon markets, landowner access or interest in carbon markets. And so I'm loving learning about wetlands and how they're different, how this is all different. Okay. And I have lots of questions, but I actually am interested in starting with the audience if people have questions ready to go. And if someone doesn't mind running around a microphone. Thank you. Oh, Nick has one. Judy and Jim, can you hear me when I speak in this microphone? Yeah.
Yes.
I can start with oh, Steve.
A question for Tomoko. They were all really great talks. I have a lot of questions, I guess, but let's ask this one. Is there enough pyrite in the system now to optimize that DIC conversion, or is that something that could be augmented?
I'm not a. Is this on? Yeah, it's on. So I think so we need to make so. As long as I think the question is there enough iron? So there's sulfate reduction that makes sulfide, and that we want to keep that sulfide in reduced form of sulfur, because if it reoxidizes to sulfate, that's when you get the acid back. So to keep the sulfide in place, one way is to turn it into pyrite. And in order for that to happen, there has to be iron available for the sulfide to react with. Generally, there's a lot of iron, and I think that one of the Reitmeier papers did a global assessment of that, and I'll refer you to that paper in terms of how much pyrite is accumulating, and maybe, where's Alyssa? There she is. I think Alyssa can say more about that too.
Is this on? Hello? Hello? Yeah. Yeah, I mean, I think Tomoko already covered it. It's really an iron limitation. So the process of pyritization is not limited by the sulfur, because there's so much sulfur in seawater. So as long as you have a saline enough system, you have sulfur in the form of sulfate that can then be reduced. But the problem is, as Tomoko said, is that once it's reduced, it's often reoxidized very quickly back into sulfate. And so to lock it away as DIC or alkalinity, you have to have the iron available. So this is something that folks are looking at in a variety of blue carbon systems, but if anyone, as most folks in the room who've been to a marsh system, you can smell it. There's plenty of sulfur there to be reduced and pyritized. So it's not really something that can be augmented unless you're in an iron poor system. So if you're in more of a tropical environment and you're in a like a carbonate dominated system, those systems tend to be both organic matter and iron poor. In which case you're going to have less reduction and not enough iron for pyritization. Hopefully that helped.
There's a question from Zoom. To all panelists, to be able to better predict soil carbon accumulation in areas without monitoring, what's your opinion, the key variables to measure? Soil accumulation, vegetation, redox, and what remote sensing data exists to do that?
Sure, I'll give it a chance. Well, I think that the first thing, to be a little glib, is to start to make better predictions. We need to start making more predictions. So that means being bold and making forecasts with the data that we have at hand and evaluating where they fall apart with new data that our models haven't looked at yet. So I think that to know how to do a better job, we have to start. To answer the question about remote sensing, we have quite a few tools at our hand for scaling things up, such as high quality LiDAR data. There are some issues with using LiDAR data in our models because there are some biases that are introduced by very dense plants that can skew elevation in tidal wetlands. But I think there are algorithms and ways that we can correct these biases. I think initial elevation is a really key thing to understand in wetlands. Having a good idea about what plants are at any given site is helpful. And of course, as my analysis showed, being able to predict what type of a system this is from a decomposition standpoint. Is this a high turnover system, or is this a set it and forget it? Once the carbon's in the ground, it's staying there. That kind of system is what really influences things and what the models are very sensitive to.
Hi. Jim, this is a question for you. So you said your model accumulates over 16,000 cores around the world, and you're adding, I think, 58. What's your process for either accepting or declining new cores into your model?
So these are a couple separate things. So the database itself is one thing, and the model is another. In fact, that model analysis, that was one core in the entire database. And so, boy, we have a lot of work to do if we're going to try to model how each core of the database formed over various time periods. But hey, I'm up for a challenge. We're working on it. You got to start with one, though. As far as what goes into the database, we are not as picky as people think that we are. In fact, we don't have any data. We don't have any. Like our main. Our main requirements are that you're okay with sharing your data with the community, that you either have or you consent to publish it under an open source Creative Commons license, and that your data has one of any given number of variables like organic matter content, bulk density, dating. You don't have to have a full suite of data. You can have any one thing. Your core has to have some positional information, latitude and longitude, even if it's rough. Your core has to have depth, explicit, original measurements. So we don't take summaries. We want others to be able to replicate any analyses that have been done on previous cores. And other than that, and it has to be from a tidal wetland, something that was a tidal wetland, or something that may be a tidal wetland one day. So a pretty big array of ecosystems that we will actually archive. Other than that, we don't have any, we don't cut things out based on methodology. We don't cut things out based on perceived data quality. In fact, we lean towards archiving and sharing the most possible, but being very descriptive in our metadata with how measurements were taken and where we can quantify things like oven temperatures for measuring loss on ignition. We encode those in our metadata so that others can make choices about what types of data they want to work with and what types they want to exclude from their analyses. So it's a big party and everyone's invited.
Hey, I'm going to ask a question. This is Lisa Marie. I am so thankful for the three of you to be here, and I noticed that all three of you brought up water tables as being important to the modeling and the observations. And so I'm curious, considering the question I got earlier about getting the hydrology right, do you have a suggestion to some of these non-tidal sites about how to manage their water table, and then also how to monitor it so that it can get into these models that you're talking about? And Tomoko, I know that's going to be a tough one for you, but you did talk about the role of the water table and the reacting, and the reactor versus repository consideration.
I don't think I talked about the water table. I was talking about more about disturbance. So I'm going to pass on this question. I'll let the other two go.
Well, I don't know about you, Judy, but I would love to see a lot more paired measurements of a time series of water levels from both open water and groundwater within wetlands, as well as redox potential and decomposition rates from litter bag studies. That would be helpful.
I think we just really need to understand the water table and in that wetland and how it relates to the upland and the other, where the wetland is going, like what it flows into. I think, a lot of people don't really see how important that is. I mean, in the Delta, maybe not so much, but like other places in the estuary where you have an upland, like Rush Ranch or whatever, we really need to understand that whole continuum of groundwater flow. That's just so incredibly important. I think that's going to become much more important if things start to really dry out more. You're going to have droughts, you're going to have big impacts. And, in my dissertation work, I studied I studied a mangrove system in Micronesia during El Nino, where there was a terrible drought, and the water actually, the hydraulic head actually flowed upland instead of toward the sea. That shows you how it was remarkable. I couldn't believe it. So we would have never understood what was going on in that system if we hadn't looked at the groundwater direction and how it's going. So I think that, people make a lot of assumptions. They think a wetland, the water table is near the surface. I think like ET, for instance, affects, don't get me started because I can talk about this for a long time, but, in North Carolina, in the Great Dismal Swamp, you have actually ET affecting water tables that's actually causing the compaction of the peat column because it's desiccating so much. So, there's a lot of impacts on peat that relate directly to where the elevation of the water table is and how it changes during a season or during a long period of drought. So that's just to get started, but I think we really need better continuous measurements and to be able to understand how the groundwater relates to the upland and also further downstream.
Hi, I had a question about both Tomoko and Judy brought up this idea of autochthonous and allochthonous carbon and its relevance for the carbon markets and things like that, and can we count it or not? Could you guys talk about that a little bit more about, it sounds like you both kind of feel like it shouldn't be counted if it's not autochthonous. but how would you logistically and like effectively manage that in a carbon market project?
I'll jump right in this time. That's really hard. I mean, that study that we did, we had to collect every kind of carbon source that was contributing and then put it into this stable isotope mixing model. And I mean, it was a big deal. So yeah, that's pretty complex. The thing is that this is not unusual to have carbon moving around and a little from here and a little from there. I guess it really depends on how much you think it is. If you have a fully vegetated marsh, you're probably not going to be getting that much allochthonous stuff, especially if it's at the right elevation. So the key that I think we really learned from the study that I did up in Nisqually is if you have something that's really subsided, it's like a bathtub, it has a ton of accommodation space. It is really like, things are going to fill in there. You would really want to be skeptical, like, where is this carbon coming from? I think that's part of it, to kind of understand the system and also understand what your neighbors are, like what kind of ecosystems are there and what kind of particulate carbon do you think they're providing to the system, and there's, different studies of things, so if you go into a system where you don't know anything, you might be pretty, that might be tough. But if you kind of understand these basic system, like the basic properties of your system, and there's been, some prior research, I think you might be able to make some pretty good educated guesses on that.
So I think this is a very complicated issue, and if I'm not mistaken, I think there are mixed messages in depending on which methodology you go to. I did come across several articles saying if it's allochthonous, you can't count it in because of the chances of double counting. And in some other methodology, maybe there was a loophole for that, I don't know. But I just want to add to what Judy just said. So there is the where did it come from? And also there's the issue of when was it fixed? So that when was it fixed, you can only get through radiocarbon. C13 tells you a little bit about where it came from, although deconvoluting the C13 signature is not straightforward because there's so much overlap across different sources. Radiocarbon has a much larger working range, and the numbers are just, it's pretty stark. It's minus 200 per mil, that's 2,000 years ago. It did not age right here, it had to have aged somewhere else. So, and that is just completely cut off from the present day carbon cycle. So I just don't see how that can be counted. And if you are counting that, I think that's a big mistake, because the reactivity of that kind of material is really slow. And when I showed that the burial efficiency dropping in big deltas, those are the places where some of that older refractory material starts to get eaten through. So labile fresh material, they'll just oxidize wherever. You can be in an anoxic environment, labile material will go. But it's the question is how much of the refractory material can you preserve over a long time? And that is more efficient in the absence of oxygen. If you add oxygen, it'll start to go. So, but anyway, so I think it's very dangerous to assume that everything you preserve there was photosynthesized recently, so let's count it. I don't think we should do that.
Well, I think that was a great final question for the session to cue us up for the next session, where Barbara Haya will be talking a little bit more about the carbon market implications of these research questions. So with that, we have 10 minutes for a quick break before the final session of the day. So we'll see you in 10 minutes. Thank you so much to our speakers. Thanks for being online, Jim and Judy. I hope you stick around for the final discussion.
All right, I'm going to go ahead and get us started as folks trickle back to their seats. I introduced myself this morning, but I will do so again in case folks were not here at the start. My name is Alyssa Griffin. I'm an assistant professor here at UC Davis in the Department of Earth and Planetary Sciences, as well as at our marine facility, the Bodega Marine Laboratory. And I'm very excited to moderate this last session of the day. I hope everyone is adequately hydrated and rested from our breaks. Our first speaker in this last session is Dr. Barbara Haya. Dr. Haya is director of the Berkeley Carbon Trading Project at UC Berkeley's Goldman School of Public Policy. She has studied the quality and effectiveness of carbon offset programs for over 20 years, working with interdisciplinary teams to study programs in the forest, energy, industrial, and relevant to today, blue carbon sectors. And we're very excited that she can join us remotely here. So with that, I will hand it off to Dr. Haya.
Great. Yeah, thank you so much for inviting me to talk. I've been online the whole day and I've learned so much. Yeah, and I'm sorry for not being able to be there, but you have my cell phone number and also email on most of the slides, so feel free to give me a call instead of bumping into me in the hallway. So I will present an article we submitted for peer review, where we studied the quality of the ACR protocol, the carbon offset protocol. I worked with an interdisciplinary research team of ecosystem and social coastal scientists to assess the quality of this ACR, American Carbon Registry Protocol, which is the protocol that DWR used to generate credits that Tyler presented earlier today. It's the main protocol for crediting wetland restoration and shift from drained agriculture to rice cultivation in California. Yeah, so we did a review of the quality of this, a comprehensive interdisciplinary review of the quality of this protocol, with the idea of, that the science has evolved a lot since 2017 when the protocol was first adopted. And I want to mention that Steve Deverall and Patty Okawa, both presenters today, were two of the co-authors of this protocol. And before launching into the research questions, I want to give a word about the motivation. So I've studied carbon offset quality across multiple sectors for many years. And what motivated this work is really the crisis of quality of offset credits on the market today, which is undermining the ability for carbon offsets to be an effective source of funding for this important project type. And most carbon offset programs today overcredit significantly. It's common for programs to overcredit 10 times or more, such as, the additionality issue. I started studying carbon offsets by studying the UN's offset program and hydropower and wind power projects in India and China, and most of those projects most likely would have gone forward regardless of the ability to sell offset credits. And quality matters because companies and governments are using these credits to meet emission reduction targets instead of reducing their own emissions, and companies are using these credits to sell carbon neutral products that aren't carbon neutral. And this harms the market too by keeping prices too low to support real, accurately estimated mitigation. And also it creates a lack of trust in the market that has led companies to be hesitant because of the reputational risks. And one thing that we've seen is companies deciding not to use these credits as offsets, but instead taking a contributions approach, that is focusing their claims on reducing their own emissions directly, and then in addition, supporting projects beyond their value chains that reduce emissions, but describing that not as an offset, but as a contribution that they made. So our study aims to inform updates to the protocol. It aims to give independent confidence to the quality of projects of this type, and to consider a way forward to bring substantially more private climate finance into this important and urgent project type. So our research questions are, does ACR's methodology accurately and conservatively estimate the greenhouse gas benefits of participating projects given the evolution of the science since it was adopted? How can projects use the methodology today to avoid overcrediting? How can ACR update its methodology to align it with the best available science to consistently avoid the risk of overcrediting? And what are the relative benefits of carbon offsets versus contributions approaches in encouraging more funding and more private funding for these critical projects? And a quick summary of our findings. We find that the protocol is generally well aligned with current science. We offer some specific recommendations for using and updating the protocol to avoid the risk of overcrediting, and I'll present the key recommendations. And we suggest two complementary approaches be used in parallel. Strengthening the ACR protocol to consistently generate high quality credits to reduce the risk of overcrediting, and to develop contributions programs that bring private funds into these projects, including activities not well suited for offsetting. So we comprehensively looked at all major elements that go into the quality of the credits. And by comparing the protocol with the latest science, and also through interviews with practitioners and researchers, many of whom are here today. So thank you for those invaluable conversations. And I will go through each one of these elements and describe how the protocol works and our main recommendation. So for additionality, ACR considers all projects, all eligible projects, wetland restoration and transition from drain agriculture to rice cultivation, considers all of those projects in the Delta to be additional. This is based on their conclusion that these projects are not common practice, that only a small fraction of possible restoration has taken place. And we see a real problem with this. So by additional, it means that these projects most likely wouldn't have gone forward were it not for the offset income. But since the 1980s, approximately 53,000 acres of wetlands have been restored in the San Francisco Bay, mostly with government funds. Much of this restoration, if the protocol had been in place, would have met the requirements of the protocol. This additionality problem. And what we recommend is a payment stacking approach be used to account for additionality. And the way that would work is if a project developer or a company that's planning to use the credits puts in 50% of the funds and 50% of the funds comes from government sources, that developer or company would earn 50% of the credits. And we believe that this approach is appropriate for this project type because substantial amounts of restoration are already being supported by existing funding sources without carbon credits. So there is an additionality issue with a blanket acceptance, clearly. There's a pipeline of potential projects vying for limited funding, and the funding is limited. And if more funds are available, more wetlands can be restored in relative proportion to the funding provided. So this approach would mean fewer credits, but it would accurately represent the true impact of those funds. And in effect, with this approach, credit prices would equal the true cost per ton of CO2 equivalents. And I welcome your thoughts and discussion on this approach. There are lots of interesting details with making it work. For baselines, first, let me just summarize how the protocol works at a fundamental level. It's basically the quantity of credits equals estimated baseline emissions and amount of carbon stored, minus monitored emissions, and well, actually, the minus is, anyway, accounting for the difference in carbon storage, monitored over the 40 years of the project, minus deductions for uncertainty, leakage, and durability risk. And the baseline is considered the average annual expected emissions over the 40-year project lifetime as defined at the start of the project. And our recommendation is to use dynamic baselines instead of a static projected baseline at the start of the project. Dynamic baselines adjust over the project lifetime to reflect changes in similar lands in the region, reducing the uncertainty that we have today about land uses and farmer choices over the next 40 years. Really, the heart of the protocol is estimating baseline greenhouse gas emissions and monitoring project greenhouse gas emissions and amounts of sequestration. And the protocol provides this range of different monitoring methods and allows project developers to mix and match across the baseline, across the project. And here is what's allowed to be used for the project, which is why for CO2 chambers can be used in the baseline, but not in the project. So basically for measuring changes in CO2 fluxes or carbon storage, you can use soil sampling or eddy covariance. And then you can use those measurements in the first years of the project to train existing biogeochemical models, such as peppermint, which Patty developed. And then that reduces the cost of monitoring over time, because you would need, once you're using models, you would need less field data. And similarly for methane emissions and N2O, you can use eddy covariance in chambers and train models. And the main point, we have a number of smaller recommendations for refining and clarifying these methods. But the main recommendation here that I'd like to highlight is the recommendation of making this data transparent and requiring monitoring data to be made available on a public repository. In part, that will help us to be able to use that data to further refine models and lower the cost of monitoring for projects in the future. And also it allows for independent review and understanding of how the carbon quantification was done. Lateral flows, we spent a lot of time thinking through that question of how can we address lateral flows given all of the uncertainties that have been discussed throughout the day. And here's our proposed solution to that. So ACR does not require lateral flow accounting in non-tidal systems in the Delta region. And our recommendation is, given the very high uncertainty in lateral flows in the Delta, to initially, actually before I say the recommendation, here's the idea, is that for measuring changes in carbon storage in soil, the two main methods are mass balance and measuring the carbon in the soil, or measuring the fluxes. If you measure carbon in the soil and the lateral flows there's more export than import, then you're likely to be undercrediting, because you're only seeing the carbon in the soil, and that carbon that you pulled out of the atmosphere that was exported, some of it will be deposited, some of it will be released to the atmosphere. There's a lot of uncertainty in how much will be permanently stored and how much will be released, but you're undercrediting because you're ignoring that part that is stored downstream. But if more carbon is imported than exported, you've got the allochthonous issue of you're seeing and you're crediting that carbon, but were it not for changing the hydrology, that carbon may have been stored somewhere else. And then it's the opposite for flux measurements, that if you measure all the net carbon being drawn out of the atmosphere, you're likely over-crediting if there's more export than import because you're crediting all of it, but some of it will be released downstream into the atmosphere. So our recommendation is, given very high uncertainty in lateral flows in the delta, we recommend initially at the start of the project monitoring lateral flows to assess whether the project area is a net importer or a net exporter, and if those fluxes are non-negligible. And the protocol defines non-negligible as greater than 3% of the credits, and to require accounting if there's a non-negligible risk of over-crediting depending on your monitoring method. So after the first few years, it really contains the need to monitor, and it reasonably ensures that you're not over-crediting due to lateral flows. And early measurements can also resolve key uncertainties to lower monitoring costs and resolve some uncertainty for future projects. So leakage can occur if your wetland restoration ends up displacing previous uses and previous production on that land. The protocol considers leakage to be negligible in the delta because production in the delta, they argue, is very small compared to the market in the US, and the impact on prices is low. However, our recommendation is to assume that all displaced products are in fact replaced in full. For example, if you displace cows, not to assume that those cows disappear, but to assume that those cows move to somewhere else. If you're displacing corn, then to assume that that corn is made up for by production elsewhere, and assume the average greenhouse gas emissions and carbon storage for a bushel of corn in the US. As mentioned earlier, to account for the risk of reversal of credited stored carbon, a portion of credits are put aside into an insurance buffer pool to be used in the case of a reversal. Our recommendation is to require project developers to contribute a portion of their own credits to the buffer pool and not be allowed to purchase credits from other projects given uncertainty about the quality of other credits, and that ACR develop a risk assessment tool specifically for wetlands. And then lastly, ACR has several requirements that prevent ecosystem harms or human harms from its projects. In particular, ACR requires stakeholder consultation and protection of the rights of Indigenous peoples. And our recommendation, very much in light of what Steve talked earlier about what he's already doing and what Grant talked in more detail about what Carbon Direct is doing in the projects that they're recommending, is to extend consultation requirements into any Indigenous communities that have traditional or customary relationships to the project region, even in the absence of legally recognized land claims. And then lastly, in my last slide, in the end, we recommend two complementary approaches: offsets and contributions, as reflected in our article title. So our recommendations, we believe, for using and updating the protocol should result in high quality carbon credits aligned with the current scientific literature that could be used as offsets. But we also see some critical challenges with the offset framework that could be avoided by the development of contributions programs to work in parallel with the offset, with the protocol generating offset credits. And I think the challenges are evidenced by the fact that there's really so far just one project that has generated credits using this protocol. So the challenges we see are funding is needed upfront to restore wetlands, but credits are generated over time. The cost per ton for wetland restoration is high compared to other project types. But the greenhouse gas benefits of these projects are small compared to all of the tremendous benefits from these projects. But the carbon market only directly values the greenhouse gas benefits. And monitoring costs are high if you're going to monitor to be precise enough to reduce uncertainty. And those monitoring costs could otherwise go towards restoration and maintenance costs over time. And these issues or these challenges we see as being overcome by the contributions approach. So in a contributions approach, private actors can contribute to greenhouse gas mitigation projects, programs, and organizations directly when the funding is needed. They can denominate their contribution in dollars rather than in tons, and that creates the incentive to procure, it reduces the incentive to procure low-cost credits and replaces that with incentives to support effective multi-benefit projects that the contributor wants to be associated with. And then there's much less need there's not as much of a need for that monitoring to get precise quantification, though you can still do that and use the protocol to generate credits if the contributor is interested in that quantification. And through our interviews and with practitioners, we've come to understand that some of the most important project activities in the Delta are particularly difficult to do as offsets. And I want to highlight two of those. Programs that support farmers in transitioning from dry agriculture to rice are hard to support as offsets because of farmer hesitancy to take on a 40-year commitment to move away from dry farming and not to be able to transition back. And contributions programs can be developed to bring private financing in to support a range of activities and programs that could support a transition from dry agriculture to rice, eventually to wetlands, even if it's unclear which activities are going to be successful, what the transition path will be, even though there's a lot of uncertainty about what's going to work and even quantifying certain types of activities. If you take a programmatic approach and a contributions approach, you can bring those funds into programs that move in the right direction and are really are for important activities that may be really hard to quantify the impact of. And then secondly, credit sales are really well positioned to provide much needed funding for wetland maintenance. We kept hearing that grants will pay for land to be purchased, will pay for the restoration, but is often not there to provide ongoing maintenance that is so necessary. And offset sales could be really ideally matched because offset income happens over time and maintenance funds are needed over time. But these would not be offset grade because of the large uncertainties in the baseline. If you're only paying for the maintenance and not for the wetland restoration, then the baseline is what would have happened were it not for the maintenance funding, and there's uncertainty about whether there would be other funding for the maintenance or what would happen if insufficient funding for maintenance is made available. What is the fate of that carbon? And then the very last thing I wanted to mention is, I envision this idea that nonprofits or the California government develop a contributions approach that could bring private funds into programs that support wetland restoration and transition to rice. And the California government currently has a really good opportunity to do this. It's now considering ways to amend its compliance offset program under its Cap and Invest program that over the summer it extended from 2030 through to 2045. The California Air Resources Board was asked to consider alternative valuation methodologies for encouraging in-state projects with resilience benefits in natural and working lands. And in that context, I think California has a real opportunity to develop a contributions program that allows regulated businesses to support wetland restoration and rice projects in lieu of buying offsets, where today so many of these, or the majority of these, of California compliance offset projects are coming from projects out of state, that most of which represent much fewer greenhouse gas benefits than they claim. And instead, those businesses could pay into a fund to support these tremendously valuable projects that have climate resilience, human and ecosystem benefits. So thank you. I will stop sharing.
Hello. Yes. Thank you. All right. Our last, but certainly not least, speaker of the day is Patty Okawa. Patty Okawa is an associate professor of biogeochemistry in the Department of Earth, Environmental, and Sustainability Sciences at Cal State East Bay. Patty specializes in trace gas measurements, specifically greenhouse gas measurements in coastal ecosystems. She developed a process-based model that we've heard mentioned several times today to predict CO2 and methane emissions from restored peatland, tidal wetlands, and rice. She also co-authored the, as we just heard about, the ACR greenhouse gas methodology for restoration of California deltaic and coastal wetlands. So with that, welcome Patty, and yeah, thank you everyone for sticking around.
Okay. Thank you so much, and thank you for having me today. Hopefully you're all still awake. But this is our last talk. So I am going to be talking about advancing wetland restoration as a climate mitigation strategy through measurements and modeling. And when I talk about measurements and modeling, it's really all couched in this theory of net ecosystem carbon balance, which we've heard a lot about already today. But the first half of my talk is really focused on this atmospheric exchange of carbon dioxide and methane in tidal marshes. And then the second half is more focused on the lateral components. And along the way, I'm going to be kind of relating all of this measurements and modeling back to blue carbon initiatives and carbon markets. So we've already mentioned this, but we have a really amazing, rich history of eddy covariance measurements in the Bay Delta region. A lot of this was pioneered by Dennis Baldaki's lab at Cal, but also carried forward by Lisa Marie, my lab, and also Steve Deverell, who was talking earlier. So across our labs, we have over 15 years of measurements in 12 sites, over 100 site years of data. It's pretty incredible. And this is really rich data from these drained, degraded peatlands to rice, restored freshwater peatlands, tidal wetlands, et cetera. It's an incredible database. A lot of it's free on Ameriflux as well. And from synthesizing a lot of this work, Kyle Hemies et al. Did this in 2019. We know from the eddy covariance database here that these drained, degraded peatlands are typically net sources of carbon to the atmosphere. On the y-axis here is the carbon balance, where positive numbers mean a source to the atmosphere and negative is a sink. So those degraded sites are in the red box, and then when you re-ret those and have these impounded wetland systems that we've talked about a lot today, they turn into net sinks. But we also then turn on the methane pump. So we have some of the highest methane emissions ever recorded from these impounded freshwater peatlands, and that's due to this high organic matter content, warm temperatures, totally freshwater. But the methane isn't simple. It's not just high all the time. These colorful figures on the bottom panel are from Mayberry and West Pond, two of these sites that have really, really dynamic annual methane budgets here, what we're showing.
But we also know that restoring tidal action can really reduce and help ameliorate these methane emissions. The bottom panel on the right is comparing these two wetlands in red and gray to a tidal site in San Francisco Bay, which is a site that I've been monitoring in my lab called Eden Landing. That's the blue line. You can see there's no methane coming out of that site. And that's a tidal site with high sulfate, but I'll talk about that more in a second. So one of my first roles in this kind of sphere was as a postdoc in Dennis's lab. I was tasked with building a biogeochemical model to help us predict the CO2 and methane budgets from these systems. So I used this network of sites, these impounded wetland sites, and built a model to help us predict these budgets. It did a pretty good job at the time, explaining 70% of the variance in NEE and 50% of the variance in methane. And then we built it into the ACR protocol that you just heard a lot about from Barbara's talk. But really importantly, we updated this model just recently, a couple years ago, to work in tidal systems, so not just these impounded peatlands in the delta. And in order to do this well, we coupled it with the cohort marsh equilibrium model that Jim talked about earlier, because these dynamic cohorts of soil are tricky to simulate. So we had this nice model that Jim Morris developed many decades ago. So we employed that here and coupled it. We also expanded the methane module to reduce methane in the presence of sulfate and nitrate, which we found to be very helpful for capturing methane. But for this, we went outside of the delta. We used a national network of eddy covariance sites. So these are very diverse tidal wetland sites, low, high elevation, high nutrient loading, no low nutrient loading, et cetera. And again, we did pretty well, explained 50% of the variance in methane, but we didn't do well all the time everywhere, and there's a lot of potential ways we can improve the model. And one example here is this bottom panel. So now we're working on testing the model over longer time periods. So this is work led by Kyle Delwich at Berkeley, but this is comparing the model here against over 10 years of eddy covariance data at Mayberry. And you can see in the beginning of the data record, around 2011, 12, 13, the model and the measurements agree very well, but then slowly over time, the methane budget really collapses and decreases, and the model really struggles to capture that. So we think there is some discrepancy between what's happening in the pore water versus surface water, and a lot of the model is being run off of surface water data. So that's complicated. So there's a lot of opportunity for improvement there. But it's an important test to be doing now that we have these incredible decadal timescale eddy covariance data. I love looking at this plot. It's just so impressive. It's also important to do because, as Jim mentioned, California Air Resources Board is going to be using this coupled model to predict all the greenhouse gas emissions and soil carbon accrual in wetlands across California. So we are building this into PCAN, like Jim was talking about, the Peppermint model and CMEM, and are going to be working on running it at the state level over the next couple of years. Okay, so the second half of the talk is on the lateral component, and luckily I don't have to go through a lot of these definitions because we've already been through this many times, but I'm really going to focus on the DIC component. There's of course DOC and POC being exported from these wetlands, but we know now from many studies that DIC is the bulk of the carbon that's exported. And this is a function of tidal inundation, carbon availability, redox, microbial activity, et cetera. And that some of this is going to be released to the atmosphere and some stored at millennial timescales in the ocean. So how are we measuring the lateral fluxes? So this is work really pioneered by Brian Bergamaschi at the USGS and Lisa Marie. We were on this project together where we learned how to do this, where you basically have
I mean, it's kind of similar to eddy covariance, where you have in situ sensors in the tidal channel that's draining the marsh. And you're measuring, instead of wind velocity, you're measuring water velocity, and these proxies for all of the lateral DIC components. So we have exosons measuring turbidity as a proxy for POC, FDOM for DOC, and a bunch of variables to help us predict DIC. And then we rate the channel. I don't know if my video is going to work. Okay, this is a little boat from the USGS rating our channel. So then we can get estimates of discharge, multiply that by our concentration of whatever dissolved carbon you're looking at divided by marsh area. And then we've been working on expanding this a little bit and maybe making it more accessible by using digital elevation models to estimate discharge at our site in Eden Landing here in South San Francisco Bay. We're also using machine learning to get at better estimates of DIC using things like FDOM, DO, et cetera. Okay, so we've done this now at Eden Landing we have 3 years of data where we have a co-located eddy covariance tower and a lateral flux station, right? So the top, and this is all work led by Imbar Amitai and many other students in my lab. So the top panel is the cumulative NEE, so that uptake of CO2 throughout the year. We have 3 years in different colors there. And then the bottom panel is the cumulative DIC. And so again, for the top panel, negative numbers mean uptake of CO2 from the atmosphere into the system. And negative numbers for cumulative DIC means export of DIC from the tidal wetland into San Francisco Bay. And what's clearly apparent is you have this strong uptake and export of carbon during the growing season. So you can see that clear downward of photosynthesis, and the greening of the wetland corresponds with when we're exporting out a lot of our DIC. But the numbers here are very different. So across these 3 years, the annual NEE was minus around 500 grams of carbon per meter squared. For DIC, it was only about 80. So I'll talk about that a little bit more in the next slide. At our site, most of this is in the form of bicarbonate, so it's about 90% of this exported DIC is in the form of bicarbonate or alkalinity. We think it's mostly dominated by denitrification and sulfate reduction, although that's something we're actively investigating and we don't know for sure yet. But it's an important question to ask. Okay, so then I wanted to put some of these numbers into context with other work that's been done in the Delta with similar types of data sets. So this is a conceptual diagram that I adapted from Bogard's paper from 2020 with the numbers that I just presented. So again, this is for Eden Landing, this classic salt marsh that used to be a salt pond. And the downward arrow is, again, that uptake of CO2 into the system. Across all of our years of eddy covariance data, it's around minus 480. We have some dated cores from this site that are in the CCN, Jim's CCN atlas, and the burial rates are around 70 grams. And then our lateral flux export, again, we think is around 80 grams. Very importantly, we don't know what the DOC and the POC export are yet, but we are very actively getting those numbers. So to compare this with Matt Bogard's work at Rush Ranch in Sassoon Bay, which has a very similar approach as an eddy covariance tower and a lateral flux station, we've now taken over that tower management, and the lateral flux station is alive and well. So hopefully we'll be getting more numbers on this soon. But it's a very different system. So for those of you who aren't familiar with Rush Ranch, it's a much higher elevation tidal wetland. It's brackish and it's undisturbed. And the export that Matt found was about 87 grams, very similar number that we've found. 90% of that was in the DIC component. So we're finding similar numbers of DIC export, long-term burials higher at Rush Ranch. And the NEE, though, is much lower. It's about 187 grams across multiple years. So this is interesting because the ratio, and Tomoko talked about this quite a bit, of the lateral flux to the NEE is very different between these two sites. So for Rush Ranch, DIC export's about 46% of NEE, while at Eden it's about 16%, so it's very different. But they both do fall within the range of reported values in the literature from other places in the world. I think one thing to really stress with Eden Landing is that it's a very low elevation wetland and it's getting inundated all the time. And so there's very few opportunities for respiration or CO2 to go back into the atmosphere. Whereas Rush Ranch is this higher elevation wetland, it's most of the time when I visit that tower, it's not flooded. So there's a lot of opportunity for respiration to occur, oxygen to get in the soil. But getting back to the carbon markets, this is 80 grams of laterally flexed DIC, mostly in the form of bicarbonate, could potentially double the climate mitigation impact of Eden Landing. Because if right now, all we could count at Eden Landing is that long-term burial, which is 70 grams. So this is a really important finding and important to get these continuous multi-year measurements of these types of fluxes. And going with my long history of working with the Peppermint model, we always then, we collect the data and then we update the models. And so we have a new NASA grant under Kevin Kroger's leadership. And we're expanding the model to include this DIC production and export. So we modulated or adapted our eco module here, and we have a DIC pool that's now being produced as a result of aerobic respiration and then anaerobic DIC production as a function of sulfate and nitrate availability in our site. And then it's produced in the wetland and then exported as a function of discharge. So discharge is actually an input to the model, so you actually need, it's difficult if you don't have measurements of discharge, but you could use digital elevation models to get at that. Okay, so these are very, very preliminary results that INBAR has been leading from my lab in collaboration with Alec Wang from Woods Hole and his postdoc Chipe. And so the top panel is the Eden Landing, DIC fluxes. These aren't cumulative anymore, they're just time series. And the data model fit. So we're doing a pretty good job at Eden Landing explaining the majority of the variation, but missing, not capturing as well the really strong import-export periods. Sage Lot's on the bottom, we're doing a poor job there. This is a site in Massachusetts that's been studied very well by the Woods Hole group. They have lateral flux data there from many years. And so we are over predicting export at that site. But I'm glad Jim went over model data fusion because that's something we'll be doing in our next step is parameterizing the model using these multi-year data sets and then doing an independent validation using the Rush Ranch data. So I wanted to end on this note of this just explosion of really great continuous data series of these co-located atmospheric and lateral flux stations across Northern California. I also really wanted to highlight Adina's work here because she has now multiple eddy flux stations and lateral flux stations running in Elkhorn Slough, and we work close with her lab. So now we have a total of 9 towers with 6 co-located lateral flux station taking, basically continuous data all the time. It's very exciting. We also have a new project that's coming soon, which is going to be in Mountain View, and we're going to have an eddy covariance tower there and a couple of lateral flux stations. And this one's really exciting because it's really getting at the baseline of restoration project for San Francisco Bay, because this is, again, salt pond restoration, but we're getting in there at year 0, right? They haven't moved the dirt yet, they haven't breached, right? So there's no tidal flow yet. So we're really excited to get some data and really constrain the baseline because there's a ton of wetland restoration going on in San Francisco Bay. and a lot of potential. So it's important to get that to support carbon market development. And we're going to be announcing that officially soon. I can't talk too much about it yet, but there will be a press release on that project very soon. Okay, so to summarize, I just want to again point to how amazing and valuable our data sets are. With 100 years of data, we know all about re-wetting peatlands. We know about this globally too. This has been shown in many places around the world. We know about methane. What we need to do is take our models and improve them so that we can predict methane over long decadal timescales, because that's what these carbon markets require and demand. And we're starting to get those types of data sets together, so we need to be really testing our models. We know that these wetlands are exporting a lot of carbon in the form of DIC, so we need to continually use our data to improve our models. That's kind of a theme in my lab. And then I didn't mention it earlier, but Alec Wang and the Woods Hole group are developing box models to help us predict the fate of the carbon that's exported from our wetlands. So we're hoping to couple our model with that model and get a better answer to that question of, okay, this is getting fluxed out of the wetland. What is its lifetime residence time in the oceans? And then make that open access and available to the carbon market community. And continually update and improve offset methodologies. Barbara's talk was amazing. We need to account for alkalinity export. That's something that's already being brought into like the isometric protocol, for example. So continually bringing our data and our models, updating them and making them publicly accessible. With that, I'll just thank my sponsors and thank you guys for your attention. Yeah.
Physically, hello. Thank you so much for that talk. I can't tell you how much it warmed my heart that the last bullet point of the last talk of the day talked about alkalinity export, near and dear to my heart. So thank you for that, Patty. So we now have a little bit of time, about 10 minutes for some Q&A specific to this last session, and then we're going to wrap up with some closing summary and more broad Q&A and discussion throughout the room. So if anyone has questions specific to Patty and Barbara's talk, we'd love to take them now.
Thank you. So this is thanks for your presentations. They're really interesting. So my question has to do with the form of lateral exchange. Is there any, how important, if any, is subterranean groundwater exchange?
So for Eden Landing, we don't think it's that important. We don't think there's a lot of groundwater there. Based on our water balance from our DEM model, it was pretty balanced. We also did some radon measurements there and didn't see any evidence of that. I know that doesn't work well everywhere all the time, but at other places it can be a really big part of it and problematic for the type of approach we're using. Yeah, it's a really good question.
Other questions?
Thank you, Barbara and Patty. I had a question about additionality in particular. And it sounded like that was just a real hammer against us here in the Bay and Delta. And then I just kept thinking about agricultural protocols and forest protocols and why why are we so, why do we have a trouble getting over the additionality aspect when they also have additional benefits of soil health improvement and water quality improvement and all these other, co-benefits? So I'm wondering how to couch our work to address this additionality question.
Yeah. So, and one thing I realized I forgot to say that Patty is the co-author on this article too. But, with the challenge with wetland restoration is that you need funding, and there is already a lot of funding. So the question is, how do you, like a lot of carbon offset projects, you ask at the beginning, would the project have happened without the offset income? And that's really hard to tell for project types where there is already funding coming into those projects. And because of the characteristics of wetland restoration, where there's already a lot of funding, but we need more funding, and more funding means more restoration, really in proportion to the funding provided. We think that a payment stacking approach is very appropriate. For different project types, you have different ways of assessing additionality. For many forest project types, there's baselines and additionality. You basically assess additionality with the baseline. So if you can assess what the forest management or rate of deforestation would have been without the project, you basically define additionality by the baseline. Additionality has been the most difficult quality challenge of offsets, and I think we do have a really good solution here that gives confidence to the credits that are generated.
I'd just like to follow up and say that doesn't mean, like, I think Barbara's solution, what the paper is putting forward, it doesn't mean that you can't do the project. It just means that if you accept some funds from the state or something, you just can't collect all of the credits because, right, you didn't pay for all of it. But one thing we've noted from our collaborators is that a lot of the funding, I think maybe more so in San Francisco Bay, I'm not sure, compared to the Delta, but in the Bay, a lot of the funding did come from the feds, and now that has dried up. So I think this funding environment it's very dynamic. So at the time that we're writing this, right, there is certain funding in some pots, not in others, and that will change as we go forward. So it's something to keep an eye on.
Great. Before we take the next question, just want to circle back to Tomoko's question. We just have a comment here from Adina Payton, who is one of Patty's collaborators in Elkhorn Slough at UC Santa Cruz. She said there is no freshwater SGD in these systems, but a lot of recirculated seawater. Thanks. Okay, another question there. Thank you.
Hi, thanks. This is Lauren Damon from the Delta Conservancy. I wanted to build on the additionality question that Lisa Marie just asked, because I think, Barbara, you were talking about it a little bit with the long-term management of projects, and I think one of the barriers to more wetland restoration, and this is specific to wetlands, not rice in the methodology, but one of the barriers to more wetland restoration, especially in the Delta, is the long-term management and maintenance costs of the projects. Yeah. And so having the carbon credits, one of the ways that the Delta Conservancy has been talking about it is these carbon credits can really help manage the wetland restoration into the future and could potentially, like we heard Tyler talk about, could help increase the carbon benefits of the projects. And so I'm just curious your thoughts on that, because I think having those credits can assure the projects can be maintained into the future and also help optimize the benefits of the carbon, or the carbon benefits of the project.
Yeah, and I agree, and the co-author team agrees that that paying for maintenance is in many ways an ideal use of offset credits, right? For all the reasons that you just said, and that Tyler mentioned. the challenge, what we propose is that it be used, but not as offsets, but it be used as contributions. And the reason we recommend that is this uncertainty in what the baseline would be, right? So if the wetland is already restored with other funds, and the offset project is paying for maintenance, what is the baseline? What would have happened without those funds? Like, we know that those funds are critical and we know that those funds are really important. But can we estimate, can we contain the uncertainty in what would have happened were those funds not made available for that maintenance? So that's why we propose that offsets be a really good funding source for maintenance, but not as offset grade credits that could be used by others to make a carbon emissions reduction claim. Does that, and yeah, I'm curious if others agree with that or what others think.
Yeah, maybe we can save responses to that for the broader discussion at the end. We have one more question here that I'd love to take before we're out of time.
Hi, thanks for taking the question. I'm having a hard time understanding why anybody getting funding to help them to build a wetland would result in additionality issues, and whether in your discussion saying that if you do receive funding that you should split the carbon credits with whoever provided the funding. It seems to me that is an agreement with whoever is getting the funding and the funder themselves, and has absolutely nothing to do with ACR or any kind of credit sales. The fact that you're building a wetland that did not exist before, and changing the background, what was there, all of the emissions that are coming off of wherever in the Delta, and then putting it into the ground, you are doing something. You're making a change, whether that it was funded through whatever the source was. So why is it not just based on the carbon credits themselves that are generated as a result of the offsets that you realize from the project? And why does it have anything to do with funding at all? That should be with the owner. I mean, as a landowner who is building a wetland right now, the costs of the ownership itself are tremendous. And moving away from traditional agriculture, which is a revenue generating source for us on the island, is taking a huge risk. And without that opportunity to generate revenue to offset some of that cost, and with the help of other sources, why would anybody ever do it? It makes zero sense for a landowner to do this. Maybe the state, but for any other landowner, how would you encourage somebody to do that if they can't take advantage of some of these opportunities and work out how that all works out with between the funder and any other source that they have? It seems like it's two separate things completely, and you're commingling the two, and it doesn't make sense to me.
Yeah, the definition of, I understand the urgency in bringing more funding into these critical projects, and sort of just wanting to get projects off the ground and wanting to avail of funding sources. And the definition of additionality is that the project wouldn't have happened were it not for the offset income. So right now, what did I say? Like thousands of acres of wetlands have been restored over the last decades, and they all would be eligible for generating credits under the ACR protocol, even though none of them, except for DWR's project, required offset income to go forward. And the definition of additionality is that you should only generate credits from projects that would not have happened otherwise. So there's clearly an additionality issue with the protocol if projects that were going forward anyway without any offset income are able to participate and generate 100% of the credits. And so then the question is, well, how do you address additionality given that. And I think the payment stacking approach accurately reflects the true impact of the funding coming in. Now, if DWR pays 50% and XYZ company pays 50%, and both decide that that those funds are enabling new restoration that wouldn't have happened otherwise, you get 100% of the funds. But if the federal government would have put those funds in anyway, XYZ company just gets 50%, right? So it is proportional to the funding. Another way to sort of ask that is, let's say the government puts in 50% and a company puts in 50%. You're saying it should be 100% of credits. Okay, but let's say it was 98% government funding and it's 2% funding from offsets. Is that sufficient? And then the cost per ton would be really low. Like, it's clearly, the current system is clearly a problem. And I think the payment stacking approach is the accurate solution to quantifying the impact of those funds.
Barbara, thank you so much. I also just want to respond to that too, because I totally hear the frustration from a landowner perspective, and I think that it's just one of the complexities and limitations of the carbon market, right? Is that ultimately it is a commodity that is being traded, and like any commodity, like for example my MacBook, Apple is going to take the majority share of the profit for that, even though there are so many value chains that go into creating the MacBook. There's one company that needs to claim the profit. And that's kind of what's happening with the carbon credit, right? Is that at the end of the day, for the company to purchase the carbon credit and put their own resources into it, they have to be able to claim the commodity, to be able to count that towards their own corporate goals. And what's tricky about this is it's all voluntary, right? There's no regulation that's enforcing these companies to do this. So in a lot of the ways, the market is setting its own terms. And so that often puts landowners or small business, like for example, small business, community organizations, at a strong disadvantage compared to other kinds of actors that can participate in this marketplace. So I think Barbara has a really great recommendation for how to think about blended finance in a system that is really challenging and complex and dynamic. And because it's a voluntary carbon market, the standards aren't set by one body. So I totally hear your frustration and the economics of it and wanting to do the right thing and participate in the land use transition and contribute to the resilience of the ecosystem and make money at the same time are noble, important goals, but the market isn't meeting you there yet. And I think that's what Barbara and Patty and others in this paper are trying to think through. If you're trying to attract private sector interest, that's kind of the terms right now, at least. And it's a incomplete, imperfect system.
Yeah, thank you. And actually, one more thing to add to what you just said is, like, I think offsets are an optical illusion that you have. In many ways, they're seen as a source of much needed funding for really worthwhile projects, and they're seen as a source of funding for those projects. And yes, you're right that farmer would make a difficult decision to switch to rice cultivation or to switch to wetland restoration and deserves to be compensated, and that's a good use of funding. At the same time, as you just said, offsets are a commodity that are being used by businesses or by governments to claim to meet an emissions reduction target. And often in wanting to avail of this funding source, we forget that or you want to preserve the quality of that credit, and that credit really represents 1 ton of emissions reductions because someone is using it to make a claim in lieu of reducing their own emissions.
Okay, thanks everybody. I think we'll wrap up this session specific Q&A. And now we'll transition to our closing summary and an open discussion where hopefully we can continue to have these really productive conversations.
Good afternoon, everyone. My name is Campbell Ingram. I'm the executive officer of the Sacramento San Joaquin Delta Conservancy. And I want to thank, excuse me, the planners and everyone for the opportunity to provide closing remarks. It's just a great honor. It's been a wonderful symposium, and I've learned a lot. And so I'm going to take a few minutes to sort of summarize and really celebrate all of the accomplishments that we've made. And then we've got a Menti question for you all to put it back to what are our next steps? What can we do next to really continue the progress that we've made? I do want to say, though, I'd like to spend the rest of the day just debating that last question, near and dear to my heart. So for those of you that aren't really familiar with the Delta Conservancy, we are a state conservancy. Our role really is to be a project developer and project implementer in the Delta and the Sassoon Marsh. In the course of our existence, we've made about $160 million of bond fund, general fund, federal dollars, and other grants available for projects in the Delta that are locally supported, really focusing on ecosystem restoration, nature-based solutions, agricultural viability in the Delta, and even economic development in the Delta. So really, we just bring resources to try to support both the long-term viability of the Delta. Nature-based solutions has been a major focus of our effort for many, many years. I really want to take a few minutes to really just highlight again and celebrate the amazing progress that we've made on blue carbon and subsidence in the Delta. And we've really just come such an amazingly long way. And then, like I said, we'll talk a little bit about how we all think we can move forward. So throughout the day, you've heard from most of the projects that I'm going to mention, but I think it helps to kind of step back and really look at it in whole and just kind of quickly summarize. So starting back in the early days, the early 1990s, a host of scientists put in a tremendous amount of effort that continues to this day. But I just want to recognize Steve Deverell started back in the early 90s and with Lauren Hastings, Roger Fuji, Brian Bergamacci, Judy Drexler, and then through time, Lisa Marie, Dennis Baldacci, Patty Owakawa, Will Horwath, and a host of other people that have, even everyone in this room, have put together decades of science that have really supported all this work that has gotten us to where we are today. And so it's truly amazing the level of effort that has gone into that and continues to go into it today. Then I'd like to recognize Brian Brock and David Julian from DWR. These guys really were the first to really get out there and start to put this into practice. They restored about 3,000 acres on Sherman and Twitchell Island out in the Delta, really took all of the science and really started at scale to demonstrate what it's all about. I used to refer to Brian as the wetland wizard, because he was one of the few people that could seemingly get restoration done in the Delta at that scale at that time. About 18 years ago, Belinda Morris and myself, we were both working for TNC at that time. We helped bring together the resources to help develop that ACR protocol that was authored by Patty and Steve Deverell. That protocol has now been used to validate one project. There's 2 more projects in the works. As we heard from Tyler earlier, we're getting very close to being able to sell credits currently with the help of Michelle and Tyler. And those credits might be able to be sold at values that are really incentivizing to Delta farmers. Sorry, got a little out of order there. We're at the point right now where we've got about 25,000 acres in the Delta that has actually been converted to rice and managed wetland. Sorry, I say converted. Probably it's about 15,000 that has been converted and about $10,000 that's currently with funds obligated and in design and in construction. And I guess I would like to point out that I think that a very small percentage of those projects would have moved forward without the expectation of the hope of having that offset revenue through the market. So we've talked about these projects before, but I want to recognize some people. The Nature Conservancy, led by Sydney Chamberlain, Jared Dixon, Michelle Passero, and Rod Kelsey and their predecessors. As we heard earlier, they've now converted 5,000 acres on Staten Island, about 4,000 acres to rice, about 1,000 acres in progress on the south end of the Delta. I'm sorry, on the south end of the island. We've helped fund about 500 acres of that. Also through a fairly significant grant to the Nature Conservancy from the Delta Conservancy, we worked with 10 Delta farmers and converted about 4,000 acres to rice just in the last couple of years as well. So that's actually convincing small Delta farmers that rice is a viable alternative to stop their subsidence concerns and be more economically viable into the future. Metropolitan Water District, of course, we haven't really heard much about the WebTrack project today, but led by Melinda Salvi and Russ Ryan and their team are converting 5,000 acres on WebTrack to a mosaic of wetland and rice cultivation. That's with a pretty significant grant from the Delta Conservancy. I think now we can start to refer to Melinda as the new wetland wizard because she's basically gotten her project within 2 years through design and permitting and just about ready to go to construction. That's pretty amazing. Also, we funded a small acquisition on Bethel Island of about 600 acres that will go into managed wetland in the relatively near future. There's also, I also want to mention that in addition to that, 5,000 acres is going into rice production on Bacon Island. The Lundberg group has actually come in and leased that land. And not only are they going to do rice, but they're going to try to do organic rice in the Delta too. So we really have a huge body of actual acreage out there as demonstration projects that are happening in real time. And there's plenty more on the horizon. We're currently working to create a funding agreement to acquire Jersey Island, about 3,600 acres just below the confluence. That would go into relatively small amount of rice and mostly managed wetland. There's a lot of salinity issues there, so managed wetland makes a lot more sense. We've worked with the California Department of Food and Agriculture and the California Air Resources Board to get rice cultivation in the Delta incorporated as a practice into the Healthy Soils Program. So that's another revenue stream that we're very excited about. We have some Proposition 4 money. We'd like to continue that rice incentive program, and joining our funding with the Healthy Soils Program funding will just allow us to achieve, hopefully, many more acres moving forward. Hopefully, I'm hoping that we get another 10,000 to 15,000 acres here in the coming years. I also wanted to recognize Lauren Damon on our staff. She's going to talk to you here in a few minutes, but she's the person who runs our grant programs for carbon, as well as just recently having brought together, along with the Nature Conservancy, a Delta carbon team. And that's a team, there's several subgroups, but many people in this room coming together to really focus on how do we continue to keep this progress going? How do we stay coordinated, aware of what everybody's doing, and then make progress moving forward? So the last thing I want to basically recognize in terms of progress is, and it was sort of mentioned earlier, but we now, through the California Nature-Based Solution Targets, we have a 50,000 acre target in the Delta to re-wet 50,000 acres of peat for the next, between now and 2045. One of the biggest challenges for the state to get that actually expressed was the oversight agencies were concerned that created an unfunded mandate. Well, I think in my view it did. It's one of our best actual mechanisms to actually help push the need for funding to get this done. I think it was kind of a brilliant stroke. So trying to recognize everybody who's been working on this for decades is of course impossible. So my apologies to anyone who I didn't get a chance to mention. In preparing these remarks, it was moving to me. When you look at it in this way, a tremendous amount of progress, decades of progress, sometimes slow, but we're getting there. We've got a lot going for us. We're a long way, really, in addressing just a very, very significant source of greenhouse gas for California and the nation, reducing the flood risk for the Delta communities, Delta agriculture, as well as California's water supply, which could, I want to be really clear here. One of the biggest benefits, we have a 150,000 acre hole in the ground that fundamentally threatens California's water system. 27 million people depend on water that is exported out of the Delta all the way to the LA Basin, Central Coast, East Bay, and about 3,000 acres of agricultural land in the San Joaquin Valley. California's economy, and I overstate this a lot, but California's economy, I think, fundamentally depends on us stopping subsidence in the Delta. Every day that hole gets deeper, the head pressure on those levees gets higher. One of my jokes through the years is, I'm surprised that the legislature just hasn't been shoveling money at this issue for a long time. So good on us for the progress we've made. So now shifting to what's next, I've got a few ideas that I want to talk about, but then, like I said, we're going to do a quick Menti and get your perspective as well. In my view, contrary to what we've heard a little bit, it's all about funding. We need more funding. We talked a little bit, I think Jim talked about the Proposition 4 and how much funding is in there. There is $9 million for nature-based solutions in Proposition 4. $9 million out of a $10 billion climate bond. So I think that really demonstrates a fundamental disconnect between recognition of the issue, the significance of the carbon emissions, the risk to California's water supply. It's the message just isn't getting through about the resource, the significance of the resource, and the amount of funding that's needed. I think to combat that, it's really incumbent on all of us to really work together to really better craft the clear and concise messages, and then really use our legislative relationships and our communication resources to try to make sure that those messages are getting to the right places at the right time in a consistent way. This is probably less about the scientific community and more about the rest of the advocacy groups within the Delta. But I really think there's a real effort that needs to focus on how do we make sure that we're advocating for ourselves effectively. In terms of the target there, obviously the Greenhouse Gas Reduction Fund is a focal point here, right? It's such a logical source. We've talked about it today. Few nature-based solutions can provide more greenhouse benefit and the co-benefits like flood risk reduction, water supply reliability, even biodiversity benefits than the work that we're doing here in the Delta. So really trying to highlight that and make sure people are aware of that when they're thinking about how to allocate Greenhouse Gas Reduction Fund. On the bright side, Senate Bill 872 just came out, and it's identifying $150 million per year for 20 years for Delta levees maintenance, and subsidence is in there, so nature-based solutions, and some restoration, some floodplain work. You can debate, and it's probably unlikely because of the political power behind the greenhouse gas allocation, that we might actually get that funding. But what's really exciting about that is that that's the Delta Caucus, the Delta Coalition, uniting around a recognized need and starting to push that need in the legislature and try to make that happen. I think, obviously, well, there's a real chance that will sort of morph into bond discussion, but I think it has the same real benefit. And I also think it's a real opportunity for us to coalesce our messaging around the need for that and supporting that. And I did want to mention too, just going back one tick, I think the contributions method is also just a fantastic opportunity. And we're actually doing quite a bit of work with some of the people that we're trying to talk to incentivize to bring more resources into the Delta to look at that model. I'm actually very excited about just how the term blue carbon is becoming is utilized in the Delta. That's relatively new. I think the blue carbon movement is a little bit further along in helping philanthropy and private investors really understand the value and importance of blue carbon and really better understand where they can invest to have real impact. So I haven't talked a lot about science. I don't want to overlook the need for their science. I mean, obviously, so much of what we talked about today is all the additional information we need. Absolutely. I think these funding sources that we've talked about here can support that. In a lot of ways, I look at it like development in the Sacramento Basin. You go out and build the houses, and then you get the money to build the levees to protect the houses. In a lot of ways, I think it's the restoration funding that can support the ongoing science too, that we need to move forward. So that's really what I wanted to say, and I really appreciate, again, the opportunity to put that out for you all. And so now I think we're going to move to a Mentimeter. We've got one question for you all, and we'll give it a minute, and then we'll just sort of open up for dialogue and get your perspective.
Just while you're getting that up, I just want to say thanks for sticking around for this. There's some upcoming opportunities to share this story, so I wanted to just take advantage of having you all here in the room and online, if we're still online, to get some feedback on having a carbon session and a couple upcoming events. So that is what I just wanted to talk about. Okay, awesome. So I think I don't have to say a lot because Campbell just laid out really the story of the Delta and carbon, and so that's kind of the story that we want to tell at these conferences coming up. The next one coming up is the Coastal and Estuarine Summit, held by Restore America's Estuaries. And this is kind of the theme that they have, and so what I'm really looking for is your all's feedback on and input on what talks and speakers would be great to have to help share the story of carbon in the Delta. And so there is a survey at the end for you to put that feedback in, and I'm hoping that you guys have some ideas for us. The talks, just to help frame what we're looking for and what input to provide on to give us this feedback is there's 13 focus areas that the event is looking for us to fit into. These are the 3 that I think that our story, the Delta Carbon story, fits into. And so just the input that you provide has to fit into at least one of these 3 focus areas. The first one being it just has to be a local story. And so obviously our work fits into the local story because this is a national conference. Just talking about our local culture and ecology and the history of the Delta, any talk that fits into that, and carbon works, coastal restoration and resilience through nature-based approaches, and my personal favorite, large-scale management and restoration. This focus area includes partnerships across state, local, tribal, and federal entities, watershed-scale strategies, collaborative decision-making models, managing risks at scale, and adaptive management and long-term monitoring. So we have a lot to say here in this focus area, especially in the Delta. And for your feedback, the summit planners for this event are looking for sessions that include finished work, which Campbell just really laid out. I think also heartwarming to me how much work we have accomplished, and so I think we do have a lot of finished work to talk about, because the purpose of the summit is to share lessons learned and strategies that are relevant and applicable to other estuaries. Again, it's a nationwide event, so they want things that can be applicable to other estuaries. We have a lot of great successes in our estuary that we heard about all throughout the whole day across policy, management, science, and implementation. So want to hear more about what you guys all have to say in our survey. And because we're at the very end of the day, I was going to go into topics, but I think Campbell just laid them all out for you all, really about our Delta story. I was going to just give you some thoughts to think about, but you just heard all of them. And so here's the link to the survey. If you guys have any questions about it, I'm happy to answer them, but it's just one quick question about who you think, or what topics you'd like to hear that we should share at the this upcoming event, Restore America's Estuaries, and future events. I'm saying events because they're not all called conferences. So that's it. That's all for me.
Thank you, Lauren, and thank you, Campbell, for those closing thoughts and ideas to keep the momentum up and keep moving forward. Thank you so much to everyone that traveled here to present or to participate, for everyone for being here, staying with us all day and contributing to this conversation about blue carbon in the Bay Delta. I'm not going to keep you long. Just a couple housekeeping. We'll send a follow-up email with these links, the results of the Mentimeter poll, and kind of some I guess, prompts to keep this conversation going and an invitation for you all to stay involved, to keep the momentum going, and take advantage of this convening and all of these great minds and data sets and resources and restoration projects that we have happening here in the Bay Delta area. So have fun at Maya's. For those of you who are going, I hope you solve all of our problems over drinks and good food. The reservation is under Lisa Marie. So in tribute to our lead scientist, I can't be there, but I hope you all have a great time. And if you beat her there, you can say it's for Lisa Marie. Okay, thank you all so much, and we'll be in touch.